Okay. So let me set up. HDMI.
On the other
Other side. Coming up. So that's a beautiful rock, but not exactly what I wanted to show you. So just a moment. There we go. Okay, so again, welcome everybody, and I'm glad to be the person to kickstart this meeting. Today I will tell you about some work that started some time ago and finally got concretized recently. However, I was asked to not just give a specific talk on a result, but an outlook on the research from my group. Now, I don't actually have a group, but I work with people, so more people altogether make a group. And that is why I added an extra thing to the original title submitted. So there will be an interlude. So I will talk about operations, causality, and memory in continuous time. We'll give you a very brief overview of this recent result. But you will see there will be a little break from the main story to tell you about another recent result. So the first result is something in collaboration with Jing Yang, who was at Nordita and now moved to China. And the second is a result with Tekla Maguire, a student from the University of Queensland. So to start with a broad outlook of what I work on and some motivations. So I actually am interested in very different topics, quite face value, quite distinct. So foundations of causality. So for example, how do you characterize and talk about causal relations in quantum theory, things like indefinite causal order, quantum space-time, so conceptual aspects of space-time when you put together quantum theory and gravity. Very applied topics like memory in open quantum systems, which seems quite disconnected from all the rest, and also very science fiction topics like time travel. So how do all these things fit together? So, well, there is some framework, some core set of topics that is sometimes referred to as quantum causal structures that underpins the study of all these different topics. And this is something that is formalized. It is treated very conveniently in a framework called process matrices or COMS or higher order transformations that I will very briefly review. So this is essentially the core of my research is about this framework and its applications to many different fields. And to give you an idea of what it is about, if you haven't heard before, the idea is to try to remove causal structure, background causal structure, from the formulation of quantum theory. So this is at the basic level is a reformulation, or in a way an extension of the way we formulate quantum theory. So to understand this, there are two ways we can typically talk about events. One is geometric sense in which an event is a location in space-time, given by rods and clocks. And the other is an operational event, something that happens. Now, in quantum theory, there is a very well-established way to describe something that happens through quantum operations. So the idea of this framework is to remove the structure of space-time, but keep the structure of events as described by quantum operations. And in doing that, you can then go and study causal structures from an operational point of view. And so to do that, we have essentially a formula that allows you to reconstruct the joint probabilities for operation performed at different idealized points in space-time or in different locations without even a notion of space-time. Now, the main aspect I want to focus on today is the fact that the framework, as it is typically formulated, assumes discrete events. So you have If you are in space-time, it means you have point 1, point 2, point 3. If you don't have space-time, it means you anyway have you have an event 1, 2, 3. And this is a limitation in my view, because there are some natural settings, for example, in quantum field theory, or if you want some approach to quantum gravity, that require a continuous space-time or a continuous set of events. And in particular, what I will focus on today, if you want to describe experiments in the lab that take a finite time, or more concretely, if you want to describe experiments where you do continuous monitoring, so you have a detector that spits out a continuous signal in time, then the current framework is not suitable. And so that's what I will focus on. So to give you an idea of what exactly we want to get, imagine you go to the quantum mall. So the quantum mall is a nice place where you can buy and shop for and see various quantum things. In particular, you might go to a stand that sells you quantum states. So what does it mean? It means it gives you something which has this on the label. So your quantum state package comes with the label that says, I'm a density matrix. It means I am something described by positive semi-definite operator trace 1. Then you can go to a different shop, that's the quantum measurement shop, that gives you P of EMs. And now you go back home and you take these two things you bought and you put them together, and by using the two labels given by the two shops, you can predict the probability to observe a certain measurement outcome given the state. And what I really want to emphasize is that these are two different shops. So the shop that sells you quantum states doesn't need to know anything about the shop that tells you measurements. And I would say this is a very basic requirement of a physical theory, where you can define your observables independently from your states. Now a question comes, what if you have to do repeated measurements? So, well, you might think I can use my projection rule, or more generally, if I want to do repeated measurements, it means I have to update my state. So typically, you will consider using CP maps. This is the way to describe quantum operations. And then you can find your joint probability for repeated measurements just by combining CP maps. However, there is a problem if now your system, your state is given, is correlated with an environment. So remember, the quantum shop is telling you, is giving you a label that is just a density matrix, but you don't know if this density matrix is coming from some system environment, some bigger environment that has been traced out. And now if after you do your measurement, your system interacts again with your environment, then you cannot use your projection postulate on the density matrix. And the reason is that the state update acts on the joint state, and so depending on what is your joint state, you will get a different answer. So how do you do? Well, one option that you can always use, and it's typically used in open quantum system, you use some system environment model, you took some interaction Miltonian, but then this means that we have to model inaccessible degrees of freedom to describe these repeated measurements. And we'll use this idea of having independent shops. So I have a shop that sells me CP maps, but then what shop should I go that gives me something that tells me the correlations between repeated measurements? So I would like something that only describes things on the system. So for discrete times, this has been solved. This is called the multi-time process. And here it's very briefly how it works. You have a shop that tells you things called process matrices, or COMs, or multi-time operators, or process tensors. And so essentially what you do is you describe your situation with a tensor product of Hilbert spaces for each time. So your process matrix is of the tensor product of input and output spaces for all your systems. And your process matrix, so the tag that the shop gives you is a positive semi-definite operator that has to satisfy a certain number of conditions to ensure that future experiments don't influence past ones. So this is the situation now. Just to remind, there are many different names of this object, of this. There are different shops that brand this thing with different names and gives you the same thing. Okay, now it's the time for our interlude. So what I describe now is the situation of causally ordered processes. Now you can just play with more general things. So you use exactly the same formula and the same structure, but you don't assume causality. So you don't assume that there is a fixed order of events and the future doesn't influence the past, and there are some interesting things you can do with this. So for example, you can model distinct causal orders with the same formalism. mixtures of orders, so maybe you don't know if it's A before B before A with some probability, and it might change in different rounds of the experiment, or even more interesting things like indefinite causal order. Now, the crucial thing I want to tell you in this interlude is that what this framework allows you to do is to recover causal information, like what is the causal order, or is there a definite causal order, through observations, which can be modeled exactly like observables are modeled in orderly quantum theory. So you get expectation values of operators acting on the joint system. And in general, you've seen one option is you can do product operations, and you can consider even more general things. Now, let's not focus how exactly you do more general things, but the most general you can do is something that acts on all sides, only input and output space, and gives you a measurement outcome. And now the question is, okay, so we say that the causal order between events is something that is encoded in the process, and we can recover it through measurements. Does it mean it's something like an observable, like spin, like energy? And this is a motivation that is often used to talk about, for example, superposition of causal orders. Say, well, if maybe causal orders is something a bit like spin, maybe there can be a superposition of causal order. And the answer, so what does this mean if that was the case, if causal order wasn't observable? It means that it should be possible to find some observable, so something like a P of M or an extension of a projective valued measure. So something that you plug in the process gives you outcome. And it should give you a definite outcome when you have order 1, 2, 3, 4, 5, a different outcome to 1, 3, 4, 5. So for each permutation, you should get a different outcome. And now the problem is this doesn't work. So it's quite interesting that if you just take two sides and you say there is A and B and they're connected by a unitary, and I know what is this unitary, then you can write that, but then you cannot do it in general. So for example, so if you have many sites and you want to be able to measure all possible permutations or possible orders, and you have a finite dimension, then this doesn't work. And also, it doesn't work if you don't know the unitaries in advance. So this is just a little interlude, a little advertisement of this result that brings us to the conclusion that causal order cannot be an observable. So this is a result that was uploaded on the archive a few days ago. Okay, going back to the main story. How much time do I have? Where do I get time signs?
15 minutes. 15 minutes.
I still have 15 minutes. Okay, going fast. Okay, going back to our main story. So we are worried about the fact that we have this formalism only for finite discrete times, and we want to extend to continuous time. So again, now we go back to the idea that each what the standard framework gives us is a way to describe repeated measurements, where I do measurement at time 1, time 2, time 3, and each measurement is supposed to take arbitrarily short time, or a time that is much shorter with respect to any system environment interaction, and we want to extend to continuous time. So I will briefly outline the result. I will not go into too much detail, but let me tell you what is the strategy here. So we will start from a constructive model, so a model where we actually give a specification of a system, an environment, and the apparatus to model the system interacting with the background environment, and the measurement as a system interacting with some measurement apparatus. So we start with a constructive model, and then we use this definition to extract some objects that act on the system alone. So we trace out the environment and the meter degrees of freedom to define objects that represent our continuous operation and our process. And then what we want is to derive characterizing properties, like we had for the discrete time, some notion of causality and other characterizing properties like positivity. And then what we do is now we take these properties, forgetting about the constructive model, and show that in the appropriate limit we can recover the general discrete time formalism. So this is the strategy. And how do we actually do it? There are a few options, but so the options I will follow is using path integral methods. I have to put out this sign because path integrals are not only slippery, but they're in a kind of superposition of being slippery. But if one is careful and knows the sign, they can be used. In particular, we'll use coherent state path integrals. It's an interesting aspect of these results that the most common path integral, which is position space, doesn't actually work for this purpose. I will not enter into the details why, but we need to use coherent state path integrals. Equivalently, one can think about phase space path integrals. So here, alpha represents a complex number, which represents a coherent state. And you can always think of this complex number as representing the position in its real component and the momentum in the imaginary component. So everything I'm describing, you can equivalently be thought as a phase space path integral, where you're considering trajectories of a position and momentum. So what the path integral tells you is a way to calculate transition matrices, to tell you evolutions, in the coherent state representation. So you have the coherent state representation of a state, it's a product with the coherent state. And you have this formula. If you start from your wave function, your coherent state wave function at the initial time, you want to get the one at the final time, then you have to perform a path integral, which means a sum over all possible trajectories that have this initial and that final time. So this alpha I here should be alpha I here. So you should have these boundary conditions where you start from some initial state and go to a final state. So again, without entering in too much details, the nice things of this formula is that you have this functional in here, and in particular you have a functional representing the unitary evolution, which is just the exponent of the integral of a classical Hamiltonian. There are a couple of different options how to actually do it, how to define the classical Hamiltonian. We use the Q function just for simplicity. And then you have an extra term, I will not discuss this in detail, that is specific to phase space and coherent state, which is something that does not depend on the particular Hamiltonian, the particular interaction. It's a kind of geometric factor that has something to do with the geometry of phase space. Okay, so that's how you do it. You plug in these functionals, and then you can propagate your initial state to the final state by taking a coherent sum over all paths. And now we use this formalism to describe the system environment meter model. So we consider a total unitary that evolves the joint system. So if you look at everything together, you have a unitary evolution. However, we specify as initial state some meter state and the product system environment state. This is required to make sense of an apparatus that independently acts on our system. And then what we want to do is to extend to the continuum the Born rule we had. So something that allows us to calculate probabilities. And so formally, the way you can think of this is that you perform a projective measurement on your apparatus, and you trace out your system and your environment. And the crucial property we use here is that the fact that the Hamiltonian is this structure, so the system and the environment don't interact directly, it means that you can write this, the functional representing the global evolution as a product of two functionals. And that's because the exponent of a sum is the product of the two exponents. Here. Okay, and then, well, basically you crank the handle and you get a Born rule for processes. So we'll certainly not go into this derivation. It's kind of standard path integral machinery, but what I want to emphasize is what you have here is now a probability for the measurement outcome. And it's a formula that now is again a path integral, but that now involves all the paths on the system. So we managed to trace out all the variables involving the meter and all involving the environment. And then we have one object that is a functional representing your process, and one object that is a functional representing the operation. And these usual phase factors, geometric factors that stay there in this version of the path integral. So the point is that now we have this idea of what the shop should give us. So the shop for continuous processes and continuous measurements should give you this. The continuous process shop should give us a process functional, which you can derive from the model. Well, it's a complicated formula, but what you should look at is that you start from this unitary system environment interaction, you trace out in path integral form the environment, and you get the process functional, while the operation shop gives you the operation functional. And again, these two shops don't need to know anything about each other to make things work. You can take one object from one shop, one from the other shop, and you plug in the formula and you get your probabilities. Okay, and now very, very quickly, okay. Very, very quickly, the properties I mentioned, I will not go through the details, I'll just flash some slides just to tell you that we can extend these properties of process matrices to the continuum. So to remind, the process matrix is an object at least on the tensor product of all input and output space, and it has to be positive semi-definite, so in this sense can be thought a bit of like a state, and it has to satisfy a bunch of constraints to ensure normalization of probabilities and also to ensure that the future doesn't influence the past. So very briefly, the fact that the process, discrete process, is on the tensor product of Hilbert input and output spaces now is reflected by the fact that the process functional is a functional on all the histories, on pairs of histories from initial to final time. So this is a formal way to take the continuum limit of a tensor product. Positivity has an expression that is very similar to positivity, and causality also has an expression that has a similar flavor to the discrete case. So your process has something that represents identity at the very end, so at the final point of your paths. And then you have a property that when you trace out your degrees of freedom from some time interval to the end, you get again something with the identity. So this identity is what ensures that when you plug in some deterministic operation at the very end, you can essentially trace it out, and so a deterministic operation at the end doesn't influence measurements done before. And the other interesting property we want to characterize is that of Markovianity. And again, the discrete form is that the Markovian process is a product of elements that describe the transition from one time to the next. And the continuous version is something similar, is the exponent of a time local expression. And what you should look at here is that the exponent of an integral is essentially like a continuous product. So it's the exponent of a continuous sum, so you can think of it as a continuous product. So again, it's a continuous version of this product formula. And now I will go very quickly through this, but the idea is that to recover the multi-time process where you have a discrete number of interactions, you have to consider specific type of operations that take a very short time. And so when you do it, again, you crank a bit the handle of the formalism, and you can get back a formula that looks like the discrete time proper, the discrete time. And the important thing, as I mentioned, is that if you now assume certain properties on the functional side, forgetting that we derive them from the system environment model, through this limit you get the corresponding discrete time property. So positive functional become positive process matrices, causality increases causality, and Markovian functionals reduced to Markovian discrete process matrices. Okay, so to summarize, well, we've seen in our interlude that causal order cannot be an observable, the result with Declan. So interesting question is, well, if it's not an observable, what is it? So it's an interesting thing to discuss. And another interesting thing to discuss is, another interesting thing we learn is that we have to be a bit careful when we talk about observables for processes. They have a rich structure that is richer than what you have for states. And then we have seen that we have derived a functional bound rule for continuous time that allows us to continuous monitoring or finite time operations on arbitrary non-Markovian processes. And interesting open question is, well, can we extend this to relativistic space-time? This will be most relevant for our RQI endeavors. And maybe can you even discuss indefinite causal order in the continuum? That is 2 question marks there. And if you want to have a bit more extended version of this talk, there will be an online seminar next week within the cost action seminars. So you can get details on the if you are in the cost action mailing list, or you can ask me the details. Okay, thank you.
Thank you, Fabio. Do we have any questions to the speaker? No questions. Rick, yes.
Can you see this type of operation being applied in quantum field theory? Like, what would have to be modified mostly? Or do you have any idea in this sense?
Yeah, that's exactly this relativistic space-time. That's what I meant, extending this to quantum field theory. So exactly, yes. So instead of having functionals that are of trajectories in time, we already know how to do path integral in quantum field theory, a functional of field configurations in space-time. Now there is this technical thing that configuration path integrals don't work, so we have to extend phase space path integrals, which might be a little annoying at first sight, but there is a way to do it. And then the next crucial thing you want to do is to extend the notion of causality. So now instead of just saying that the future cannot influence the past, you want to encode the light construction there. And yes, I have some ideas how to do it.
Would this then also be an option for the result of causal order not being an observable to be changed by having basically the relativistic regime allowing for that?
I don't think so. There is a technical detail that has not much to do with continuous time, but with the continuous variables, because this not being an observable is about finite dimensional systems. So if it starts to be infinite dimensional, things are a little unclear. But I will say that relativistic structure doesn't help you in that respect. So it seems to us that the way causal order fails at being an observable is a very basic thing. So more generally, causal structures, whatever, if you define it as a partial order or as a directed acyclic graph, in general, we expect these are not observables. The point is to infer things about causal structure or causal order, you have to know the specific processes. So you have to know not just that ask if A is before B, but what is the specific unitary or channel connecting A and B.
Okay, let's thank Fabio again. And the next speaker will be Guilherme Franzmann, who will tell us what is an independent system.
All right, I guess I can start. Thanks for the invitation. It's really nice to be here, and it's nice that I was part of the RQI circuit last time here as well, and I agree that the room is much fuller now, which is nice. Anyway, so today I want to talk about the notion of subsystem independence in perturbative quantum gravity. A lot of this work is based on a review that's being written within the concept of this collaboration called eMERGE, and mostly Jan, Govaki, and I are leading the effort. Okay, so let's start some motivation. We like to think that there should be a notion of background independence in our fundamental theories. There is also some notion of principle, kind of like principle of relationality. I'm not calling relativity because I don't want you to think about space-time only. So things should be somehow relational. We like to think like that. And because of that, we learned that there is some sort of like breakdown space-time in time and space is not particularly absolute. And in fact, it's dynamical as well. Now, there is a nice paper by Zurek from 2007 that he postulates the zeroth axiom of quantum mechanics that usually you don't read quantum mechanics textbooks, which is the world consists of systems. And so then you can start thinking like, well, are systems absolute in a way that challenge background independence and this idea of relationality? Or rather, the way that you think about quantum systems in the context of like Hilbert space assigned to them, maybe is also something that shouldn't be absolute, but should be somehow relational, maybe even dynamical. And moreover, my own research, which is a lot in space-time emergence, if I want to think that space-time emergence, or maybe space, not so sure about time, is emergent, and we infer space and time from physical systems, and we know that space-time has all those nice things about being relational, perhaps there is something about the way that we should understand systems in a different way that we do nowadays. Okay, so the take-home message is going to be very simple. It's going to be this, that when we start in thinking of not having gravity and just normal book quantum mechanics, everything goes really well. And as we push things towards quantum gravity, we have a lot of questions that remain unanswered. And hopefully by the end of the talk, you're going to appreciate a bit more about the kind of problems that we face. Okay, so let's start with no gravity. By the way, my slides are going to have math and stuff. You can always come back to them, but I'm going to keep more narrative. And if you have questions at the end, we can actually come back and look more closely to the notation and to the mathematics. So what's a quantum system? Typically, we think about quantum systems by having some kind of Hilbert space. There is typically some state space, some convex set. We're going to be thinking about density matrices here. And there is also some space of observables. And typically, by having this triple, we characterize, at least kinematically, what we mean by a quantum system in quantum mechanics. So naturally, you can ask, what is a subsystem in quantum mechanics? And a subsystem is going to be just like a system, but now you have to somehow be able to talk about that in the context of an enlarged system. And typically, one way to do that is to think that you can have your subsystem, its algebra observables, for instance, embedded into this enlarged quantum system. You can define those embedding maps where you take observables from your local subalgebra and now embed as a global observable. And you can do something just like that, basically taking the dual of that and define also restricted or density matrices. In the case where you do have a factorization of Hilbert space, that's what we call a reduced density matrix. And typically we define them by just impose the expectation value as seen from the subsystem point of view can be now written in terms of the quantities defined over the global Hilbert space. And again, as I said, typically those maps, they become just tracing things out in typical quantum mechanics. Naturally, the question is, okay, so I told you what a subsystem is. How do you know you have more than one subsystem? And then we get into the notion of independence. How can we talk meaningfully about having different subsystems? And it turns out, as you can see here, things start to become more interesting. There are different notions of independence that we rely on when we do quantum mechanics, quantum field theory, quantum gravity, and they are more or less connected. And I will try to convince you that when you do quantum mechanics, textbook quantum mechanics, they all collapsed into this single structure that we call the tensor product structure. But you can disentangle all those things, and we better do, because we're going to go to more complicated regimes where those things don't become that equivalent anymore. So let's start. Just let me say that also everything that's in black here are things that you can think more operational, while the things that are in white, like what's a tensor product structure, is something very abstract and algebraic. But the things which are here in black are things that you can think as if you go to your lab and you have your notebook, your data, and you want that notebook to have some properties when you gather data. And those things here, they encapsulate that. I'll explain why. So the first one, let's focus on statistical independence, which is also sometimes known as state preparation independence. The idea that you can go to the lab, and if I have system A and system B, I can prepare their states independently. And so statistical independence means that if you have two subsystems, they will be statistically independent. If for any states on each of those subsystems, you can find a global extension that when you restrict this global extension to each subsystem, you recover the state that you wanted to have prepared for each of them independently. So we can write everything in a more succinct way, and you can come back to that later if you want to understand the notation a bit better. But basically, the idea is that we demand compatibility of the marginals. When you take the marginal probability distribution, they should match up if you start with this global extension. Naturally, you can think about failure. When does that fail? You could have thought that you have a system like a cube, and somehow you thought that the different corners of the cube were independent subsystems. And then you want to prepare this corner to be up and this corner to be down. Then you find out that you cannot. And you cannot because there is a constraint. So whatever states that they have that you're going to prepare those corners is going to depend on this enlarged system, the cube or the die that you throw. And therefore, you do not have, for every possible state that you want to prepare for those, a global extension. And here, just to give you already the intuition that in the presence of a constraint, this kind of a notion suddenly becomes non-trivial. You can ask even more. Not only you can think about statistical independence, you can think about statistical independence in this product sense. And this is just a fancy way of saying that not only you want this global extension to exist, but it should exist in a way that is a product state. So basically, you can just write down the definitions. This is inspired on the idea of independence of events. When you just think about pure probabilistic theories, that you have, if you have two events that are independent, the joint probability factorizes as a product. And you can demand that also for your global quantum state, your global extension. That for every possible states in each subsystem, there is a global state such that its joint probability distribution over the observables of each subsystem factorizes as a product. And naturally, it is a stronger notion than the previous one. And so if you do have this notion, you imply that you do have statistical independence. So I've been focusing a lot on the existence of states. This was the lower part of this diagram. We can now look to observables. And we have two different notions. One is joint measurability. And so joint measurability means that if I have two pairs of observables for each subsystem, then there exists another observable defined on the global Hilbert space, such that you can use that global observable to derive or recover what would be the statistics associated to each of those observables. And here, of course, it's just, again, just notation and math, how to define those things precisely. But what I want to tell you is that you can show that if you impose joint measurability, that implies that those algebras, they have to commute. And you could also have thought about that in a simplified way, just by thinking that if you think about this as observable to self-adjoint and this self-adjoint, the product is not self-adjoint unless they commute. That's a quick way to think about why this should be true. You can also think about non-disturbance. What does it mean to make a measurement on one system that does not disturb the other system? And of course, in the literature, this is more usually thought about in the context of non-signaling, but we don't need still to embed any of this in space-time. And so the idea is that if you make a measurement on one system and you do a non-selective state update of the state of the global state based on that measurement, then just can apply. So this is the general state update. You can apply now for one of the systems, and then you demand that the statistics of every single observable of the other system remains the same if you consider the original state or the updated state. And of course, this just means that you can show actually that if you impose that for every single element of, or every pair between the two algebras, that also implies that the algebras commute. So here we talked a lot about expectation values or data that you can gather. That's why we're covering all of those. But we already saw that we have this commutativity appearing here, which can be typically is called observable independence. So just to flash the slide, we can take the embeddings of those algebras into the large Hilbert space, and we say that there is a notion of observable independence if the subalgebras commute. So all of that is probably quite familiar to all of you. And the key point of this diagram is to say that all those different notions, they can be in the context of having finite-dimensional quantum systems. You can show that by just imposing that you have a tensor product structure, everything follows. And that's why maybe we don't think too much about that when you're doing quantum mechanics. Now, just to recap, in case you don't know, when we mean by tensor product structure, basically this idea that you can factorize your Hilbert space in different factors. And then there is a formal definition of how this factorization works, because it's not just a unitary that takes this Hilbert space into this isomorphic Hilbert space, but actually is a unitary modulo, the fact that you can rewrite this unitary or those factors as with local unitaries. So really, a TPS actually defines a particular equivalence class of operations that you do, or mappings that you do between this global Hilbert space and the isomorphic one. And then there's a theorem that goes back to Zanardi and others in the early 2000s, but it can go all the way back to literature in like algebraic QFT in the 60s, 70s, that if you have some interesting properties such as that you exhaust your system by doing this factorization, then you can show that it is if and only if you have a tensor product structure that your observables commute and can be embedded as von Neumann algebras on a given Hilbert space factor. Okay, so if we go back to the diagram, we can actually write down everything quite mathematically, and this is all very nice. And so just a recap, this is the central notion that we're talking about here, which is defining our quantum systems, and it's guaranteeing us that we can make measurements which are independent across those systems, and guaranteeing that we can prepare states independently across those systems. Now, of course, I just said a lot about quantum mechanics, but it turns out that by demanding those notions of independence, preparation of state, and measurements, you can actually apply this very same construction across classical mechanics, and then there you have the Cartesian product, not the tensor product. Quantum mechanics we just reviewed with the tensor product, but you can also do that in quantum field theory, and things start already becoming a bit more fuzzy. I won't go into details, we can come back to that later if you want, because there not only you have to rely on the notion of commutativity, you also have to rely on some more abstract algebraic properties, which has to do with the fact that local algebras in quantum field theory, they're what we call, they're not type 1 von Neumann algebras, they're type 3 von Neumann algebras. But we won't be covering much of that here. This is to tell you that everything that we did so far is quite well generalizable in the context of QFT as well. But I'm interested in gravity. And so if we go towards low energy, perturbative quantum gravity, things start becoming a bit complicated. All this picture that looks quite nice. So it turns out that if you think that you can model low energy quantum gravity as a quantum field theory, and you want to canonically quantize this quantum field theory, there are some results that start to prevent us from thinking about those properties that were quite nice, that allow us to connect all those things together. One realization comes from this paper by Donellis and Giddings in 2016 that basically shows that if you start with what would be space-like separated operators in your quantum field theory, if you have some scalar field and you expect them to commute, it turns out that they are not gauge invariant operators. If we have time, we're gonna go back to that. And then when you make them to be gauge invariant, meaning that they're diff invariant under the diff group, linear diff group for perturbative quantum gravity, even when things are space-like separated, they no longer commute. There's another interesting result that goes back to Don Marov 2008, and also Raju 2021, that shows that there is something called holography of information that happens in the context of perturbative quantum gravity, and that undermines the notion of statistical independence that we had before, of you being able to prepare states independently. We were going to be now looking at those two results with a bit more detail. But just to already highlight that this result and this result, each of them are kind of undermining these different operational notions of independence. This is undermining things that having to do with our observables and commutativity. It was like the top row in our diagram before. And this undermines the notion of statistical independence, state of preparation in low energy quantum gravity, which is undermining the bottom part of the diagram. Yes, so this is what I just said. So let's quickly review how that happens. If you think about low energy quantum gravity coupled with a scalar field, you can just write down your Lagrangian. You know how the linear diffs change or transform your metric. You also know how linear diffs transform with a scalar field. That's how you can see the scalar field is not gauge invariant. You can start with two space-like insertions for this scalar field, which commute, but they're not gauge invariant, as I just said, because each of them transform. And then you can try to now build an operator that's going to be gauge invariant. This is called dressing. There are different ways of doing the dressing, but all of them arrive at the fact that once you do make the dressing and make those operators gauge invariant, it turns out that the dressed version of those operators, they do not commute anymore at space-like separated regions. This is just showing how the dress operators look like. It doesn't matter so much. The crucial point is that you could ask why. I just said that in the QFT picture, everything seems to work fine. What's happening with gravity in this canonical perturbative regime that's preventing gravity from satisfying the typical dressing scheme that we also apply for Yang-Mills theories? And it turns out that if you go back to this dressing, what appears here is not only the metric, but also derivatives of the metric. And it turns out that this is typical that for any kind of dressing that we do when you have a gauge theory, basically in the dressing, the connection appears. But what we do in normal gauge theory is not gravity. We quantize the connection. But when we quantize the perturbative quantum gravity, we quantize the metric, not the connection. So if you go back here, for normal gauge theories, we do not have this term. We only have the connection or the gauge field here. While for gravity, we have both the metric and derivatives. So you can expect that when you hit this operator with another operator, which is going to be non-localizable because they are having integrations here, at some point you're going to be hitting the metric with its derivative, and that's going to pick up a contribution that you wouldn't pick up if you're doing just normal QFT. And then there's this thing about holography of information. So there is something quite striking that whenever you have a diff variant theory, basically the Hamiltonian of the theory can be written as a sum of the constraints acting on the bulk plus some boundary term, assuming that you do have a background in which there is a boundary or an asymptotic region. It can be flat. And so that means that all the transformations, all the time evolution of all your operators, basically, if they are operators that are gauge invariant and the constraints annihilate them or commute with them, all the evolution is coming from the boundary term. And so Marov, in 2008, used this to prove something quite impressive, which is, so this is like a very quick summary of the proof. The proof, of course, has many more details, but I can give you a quick gist of what's going on here in this diagram. So the idea is to think that you have your gravity theory, and you are in past nu infinity, and you have all the different possible modes that you can send off from past nu infinity. They can bounce here and go back all the way to future nu infinity. You see that I omitted the future region here because actually Marov, in his paper, he's thinking about a black hole background. So there's a black hole here, and a lot of those modes are just going to go inside the black hole. And the question is, where's the information? Of course, it's motivated by the information paradox. So what happens here is that because you have this boundary Hamiltonian, basically what you can do is you can take any point of past nu infinity, any radiative mode here, and you can translate them up and down. And in particular, you can translate all the way down here, in which you're far from this future region omitted, and you can think that you're in a flat regime here. So you translate them back, and then you evolve with equations of motion to a point in future nu infinity. And if you push the limit in which you translate everything back all the way to the asymptote past infinity, basically you collapse all the relative information that you have here around a small little region at spatial infinity. And this is what's called holography of information. That actually you don't need to have access to every single point here or relative mode going off, because they are all related by this translation being implemented by the Hamiltonian. And then you can actually encode all the algebraic information that would be present in the bulk in a small little region around spatial infinity. So I'm running out of time. Let me just say that if you do have, not surprisingly, if you do have now basically a representative of the algebra of the bulk at the boundary, you can use that boundary algebra to fix your state completely. And if you do that, then basically you say that, well, this is just saying what I just said, that we have this holographic information, that you can use the boundary algebra to fix your state of your whole quantum system. And maybe that shouldn't be surprising to you that this would lead to a failure of statistical independence, because you could think that you had a chance of fixing your quantum state inside a region with different possible configurations, while you have a given fixed state outside a particular region. But by using the holography of information, basically you can show that if you do that, you arrive at a contradiction. And your state, as soon as you fix a state at an outside boundary region, you can fix the state inside as well, which is basically what we didn't want to have if we demand a state preparation independence that we start with before. I'm running out of time. Just want to say that there is a sense in which this picture that we had before is lost. And the question is like, what would be the lesson and how to augment this or implement this in a better fashion. And maybe for you, maybe you've never seen this before, the question should be like, why should you care? I mean, I care, I've been doing that, and I like those things, but why should you care? And is there a sense in which we should care, given the kind of physics that we do? So let me give you 2 reasons why you should care. Not sure if anyone here does cosmology, but I'm sure everyone is familiar with this. And we look to the cosmic microwave background, and we are looking to infer from these statistics different properties of what happened in the early universe. And it turns out that if you go and we study cosmological perturbations, we are modeling this using low energy perturbative quantum gravity. And typically what we do, we say that we look to different points of the sky, and we say, they of course are statistically independent. They were prepared in a state that they were independent, and we run the statistics and we model the theory, and therefore we ask for something like inflation to explain why they are so correlated. And similarly for when we make measurements across the sky. The second thing that you might make you care about this is the fact that nowadays we are also trying to probe in tabletop experiments low energy quantum gravity. And once again, we are using low energy perturbative quantum gravity to model those experiments. And hopefully everything that I told you so far should tell you that this picture where we just write tensor factors when gravity is involved shouldn't be quite there. But of course, if you open at least the original papers on gravitationally induced entanglement experiments, there are tensor product structures everywhere, and there is a notion that you can prepare states which are in a product state for your initial state for the 2 independent masses. So I think that would be the reason of why you should care, is that we are already at a regime or a period of time in which we're trying to probe regimes in which low energy quantum gravity might play a role. And the big question is like, okay, so how do we improve everything that we did so far so that we can talk meaningfully about subsystems, about things getting entangled, so on and so forth. Here just leave some food for thought, which is the fact that we learned, as we start with the talk, that space and time were not only were not absolute, but were also dynamical. And the analog of space and time, in my opinion, in the Hilbert space level, is what we call a subsystem. And so the question is, how can we maybe improve, and do we need to improve the fact that we rely on these absolute structures in Hilbert space when you think about subsystems? And if not, if we allow that to be more relational or dynamical, what can we learn with that? And with that, I finish here. Thank you.
Thank you, Guilherme. Are there any questions? Quick questions. We don't have much time. Sebastian.
So in some of the results relating the different notions of independence, you had assumptions about the dimensionality of the Hilbert space, for example, and also the boundedness of the operators. And even in quantum mechanics, that sometimes has to be extended. So what does this mean then for the different notions of independence in quantum mechanics already?
Yeah, very good. So I presented the most vanilla possible diagram, and there is extensions to pretty much everything that I discussed. And if you're curious to actually learn more about that and how that applies to more general quantum systems, even in the concept of pure quantum mechanics, there is an excellent review by Stephen Summers from I think 89. It's a thick, big review, extremely technical, but pretty much everything that you want to know that goes beyond von Neumann algebras, C-star algebras, and other more sophisticated quantum systems, that's the place, I guess, you could start with. Happy to also give you more papers. Yeah.
Okay, let's thank the speaker again.
Thank you.
And the next speaker will be Perche, who will tell us about theoretical, operational, and experimental progress on vacuum entanglement.
Thank you. This guy. Where's the clicker? Okay, where's the clicker thing here? Do you have it, or do you know how to use it? Yeah? This one?
Yeah.
Oh. No, it's USB-C.
Okay.
Thank you. Great. Sorry, I'm not using my computer because my computer is busy, so I have no idea what's going on here. Maybe I need your help again, Marcus. I don't think the adapter is seeing it very well.
The HDMI was working.
Well, okay, now it's working. Okay, good. Oh, but it's, yeah, it's not on the correct mode. Great. Do you have a way of doing this now? Good. Cool. Perfect. Hmm? Yeah. I can try, but it's not working. It's just super slow. It's fine, it's fine, it's fine. I'll handle myself. I think it's just delayed. Or, oh no, I'm just going forward. It's gonna work, don't worry. Okay, should I start? Okay, good. So I have a timer, so don't worry about the time. Okay, good. So, all right, yes, I'll talk about some progress in vacuum entanglement. So let me start with some disclaimers. So I was invited to deliver this talk at the RQI circuit here, but I was seriously considering not accepting this invitation because it's kind of not easy to think about the whole broadcast, to doing the thing and then coming here and hopefully everything is working there, but there's no way for me to check it now. But okay, good. Regardless, so I decided to accept it in the end for two main reasons. So one is that the next two talks are by my master's students, and they'll both talk about quantum field theory and probing quantum fields. So, and the time is fairly limited. So basically, I'm going to try to introduce a couple of these concepts there during my talk. And the second reason is because I'm very interested in these things that I'm going to present here anyway. So it's a pleasure to actually talk about this. Okay, good. So the disclaimer is basically don't expect much of this talk because I did not prepare this. I have no idea where it's going to fit on this time or not. But I'm very interested in the research, and hopefully I'm going to be able to convey a little bit of this excitement to you too. So the talk will be split in 4 parts. So first I'm going to talk about local quantum field theory, this local approach to quantum field theory, just to give some context. Then I'll talk about vacuum entanglement in QFT, which is the central topic of this talk. Then I'll talk about these local probes in quantum field theory, which is the thing that I've spent most of my time, my academic life, doing research on. And finally, I'll mention some experiments that can actually implement analogs, or not necessarily analogs, but systems that are equivalent, or interactions that are equivalent to these local probes in QFT. So, because time is finite, let's start. Oh yeah, sorry. And just to explain the title of the talk, so this is what I would call the theoretical progress, and this is what I would call the operational progress, and this is what I would call the experimental progress. So basically, I'm going to try to mention or talk about 3 papers here in 20 minutes. Okay, so now, because time is short, the approach that we're going to use to QFT is definitely not the high energy physics approach. It's going to be this approach of talking about local degrees of freedom of quantum fields. And what I mean by this is basically this idea that comes from algebraic quantum field theory that assigns to finite regions of spacetime, or if you will, causal diamonds in spacetime effectively, local degrees of freedom. And these local degrees of freedom are basically encoded through these algebras of observables. So to each causal diamond, we're going to assign algebras. And you can think of these algebras as being generated or containing everything that can be built from these smeared field operators, or at least in the case of a real scalar field, right? Everything we're going to be doing here will be for free field theories. That's why there's a little asterisk right there on the A. But the idea is that given an algebra, if you consider functions that are given a region, if you consider functions that are supported within that region, then this smeared field observable is like somehow a regularized version, a localized version of the field operators that can be probed. And the idea is that the expected values of these observables at a given state will encode these local degrees of freedom of the field. As Guy mentioned, basically in quantum field theory, the idea is that you want to implement causality through imposing that observables that are localized at space-like separated regions commute. So my light cones are 45 degrees here, which means that basically the idea here is that if you have a function supported here, a function supported there, these are space-like separated. Thus, we're going to enforce that these operators commute, so that measurements will be compatible, if you will, but this is a longer discussion. And the other approach to algebraic quantum field theory is where instead of considering these causal diamonds and these full algebras in spacetime, instead of that, what you can do is to fix a surface, and you can refer to initial values, or if you will, the field and momentum operators at the surface. So here pi is this conjugate momentum to the field, or the partial derivative of the field. And now what happens is instead of smearing them in regions of spacetime, you consider functions that I'm denoting as capital F and capital G that are supported within this spatial slice, spatial part, okay? And from these, basically, you can also build algebras that are equivalent to these mirrored algebras. Actually, the relationship between the two is given by this equation. There are some things that would have to be defined, but basically these two descriptions are fully equivalent, okay? And this is everything I wanted to say about QFT, because again, time is finite. So basically, the summary is that each finite region of spacetime contains infinitely many degrees of freedom of your field. And these degrees of freedom are basically associated to these mirrored field and momentum observables, or if you will, these 4 smeared fields in each one of these localized regions. And these two descriptions are equivalent. And space-like separation basically implies commutation of these observables. So this is the summary of QFT. So let's go to the main topic, which is entanglement in QFT, or more specifically, vacuum entanglement in QFT. So what happens here, let's start with the simplest case, or the case where we know a little bit more about, which is the case where we ask about how much vacuum entanglement is there between one region and the complement of this region, okay? So this is a simpler case because the idea is the vacuum in the whole spacetime, or in the whole surface, if you will, is a pure state. If it's a pure state, there's a bipartition, which is A and its complement, which means that now, if you compute the entropy of the reduced state, this is an entanglement quantifier for pure states. And if you compute this entropy of the reduced vacuum state to a finite region, what you will find is that this entropy behaves basically proportional to the area of interface, the spatial area of interface between the region A and its complement. And there's this cutoff here, which is kind of, it's epsilon here is a UV cutoff. And if you take this UV cutoff to 0, what you find is that this entanglement between one region and the exterior goes to 0, to infinity. Which means that in principle, if you're able to couple arbitrarily close to the boundary at arbitrarily high energies, you'd be able to extract an infinite amount of entanglement from the vacuum, right? But of course, this would require infinite energies and all of these things. Good, but what I'm really interested in isn't in how much vacuum entanglement is there between one region and the complement, but how much vacuum entanglement is there between two regions. So now you might notice that the argument of the vacuum being a pure state, and then you reduce it and compute the entropy, doesn't work, because although the vacuum of the full surface is a pure state, when you just restrict yourself to A and B, now this restriction gives you a mixed state, effectively. You have to regularize things. You can't really talk about states that loosely in quantum field theory, but this is the intuition. And then, well, now you have a mixed state in a bipartite system. And, well, now you can't just use the entanglement entropy to quantify entanglement, right? You need a little bit more, to work a little bit more to get that. So how do we do this instead, right? So there's this Gaussian approach that started being more and more, used recently. So let me explain the idea. So remember that these local degrees of freedom of QFTs are encoded in these local algebras of observables. So basically, if I pick a causal diamond or a finite region of a given Cauchy surface, and I consider functions such that the smeared field and momentum operators, basically for each choice of function f, I get independent modes. What happens here is that, there should be an I there, by the way, but I get independent modes. Then what happens is I can encode all of the degrees of freedom associated with these modes into these smeared field operators, and basically map my problem into a symplectic space, which is finite dimensional, encoding all of these n modes of the full system. So the idea would be to do something like this, and then in particular, the idea is that then the degrees of freedom would be fully described by their Wigner function, which is just a function in phase space. And for the vacuum or for Gaussian states overall, basically it's enough to just compute all of the expected values of products of field, momentum operators, giving you a covariance matrix. And from this covariance matrix, basically, you can describe all of these vacuum degrees of freedom up to this given cutoff that you introduced based on the modes that you considered. So it's a way of simplifying the description of your vacuum state, of your local vacuum state, of these degrees of freedom of your vacuum state. So if we want to quantify entanglement between two regions, what we do is we pick functions here, enough functions here, and enough functions there. We compute all of these expected values that are relevant for the covariance matrix. We build this full covariance matrix. And now, for instance, one way of quantifying entanglement between the regions would be to use the logarithmic negativity, which basically only involves computing eigenvalues of this matrix with components that you have. And this will give you how much entanglement there is between all of the degrees of freedom localized in A and B that you described using these functions. Or more explicitly, if you pick a basis of functions for OA and OB, now a basis, L2 basis that is normalized, then basically what happens is these automatically define independent modes between the two. And you introduce this cutoff, you can compute the entanglement between the two regions using the logarithmic negativity. And what's also interesting about this approach is that you can find what are the most entangled modes between these two regions. And this is recent work based on many papers. This is the reference that I decided to put here by Natalie Kelko, Beck and Savage, the KBS entanglement consolidation algorithm. And I am working with Patricia, my collaborator, in basically finding these most entangled modes between two regions. So what's the idea with Patricia? So consider two spheres in three-dimensional space of radius r and separated by a distance d. What you do is in each one of these spheres, you find the basis of eigenfunctions of the Laplacian operator. So this will be the functions that will define these local modes. Then what we find, introducing a cutoff, is that this is the shape of this mirroring of the field and momentum operator in each one of these two spheres, looked at in the xz plane, where z is the separation between them, which are these most entangled modes between these two regions. And these contain like 99.9% of the entanglement between the two regions, based on some previous studies. So basically, I would argue that this is the first step towards understanding fundamentally this local entanglement structure of quantum field theories. And this paper should be coming out soon because we already have all of the results, and we're very excited to basically find these most entanglement modes and hopefully couple to them and extract entanglement from the vacuum, if you will. Cool. So, step 2, local probes in quantum field theory. How do we actually access vacuum entanglement? How do we probe these local degrees of freedom that live in these causal diamonds? So the idea is to consider probes, probes that couple for finite times in finite space-time regions. And these probes will effectively see the degrees of freedom that live in the causal diamond that contains the region that they couple to. They will see the observables that live in these local algebras. So what are these probes? These are particle detector models. And whenever I introduce these, I tend to put this sentence here by my very first paper. Eduardo was the one that wrote it. So from the retinas of our eyes to the solid state center source in the LHC, we never measure a quantum field if not by coupling something to it. And the idea is that these particle detectors, these UDW detectors, are the theoretical framework for the something that we couple to quantum fields to operationally extract this local information from the fields. More concretely, a particle detector is a localized quantum system that couples to a quantum field, often for finite times if you really want to get information about these local algebras of observables. Even more concretely, the simplest model, or the most used model for these particle detectors, is this two-level UDW model. So it's basically a qubit that interacts with the field, and this is the interaction Hamiltonian density. There are many terms here, so let's break them down one by one. So the first one is just a small coupling constant. We usually do perturbative things with this, although Sebastian will give us a counterexample later today. The other one is the interaction region, which is where in space-time the interaction is localized. This is what defines these local algebras that these detectors are coupled to. This is basically a time-evolved sigma X matrix, which is the observable of the qubit that is coupling to the quantum field. And omega here is the energy gap, so how fast these or the strength of these internal dynamics, right? The energy difference between these two levels. And they're coupled to this quantum field. So it's a very simple model. It's a qubit coupled to a quantum field, but it turns out that this can actually reproduce numerous physical systems. A couple examples are here, but it's a very powerful toy model in the sense. It really captures the essence of locally interacting with quantum fields. And of course, very important for us, it samples these local degrees of freedom of the local algebras, if you couple them for finite times. So just to motivate this a little bit further, there are many uses of these particle detector models. So they can be used for probing the temperatures of quantum fields, the under-Hawking effects, all of that. They can operationalize measurements in quantum field theory, which is good from theory and experiments. They can access the field correlations effectively, and Sebastian will mention a little bit more about this in 2 talks. They can be used to implement the quantum energy teleportation protocols. They can be used to transmit information without energy exchanges. They can be used in relativistic quantum computing. But most important for us here, they can be used for quantifying entanglement in a quantum field, right? So basically the idea is that we want to couple these 2 probes to extract entanglement from the vacuum, say. And this is the protocol of entanglement harvesting. So we want to couple these 2 probes into causally disconnected algebras to independent regions, right? Very important, so that we're really sampling independent field degrees of freedom. And we want to extract entanglement from these 2 regions. So from a fundamental perspective, you can use this to lower bound how much entanglement there is between the 2 regions. But also from a practical perspective, I mean, this is the fastest possible way to entangle 2 systems. They don't have to communicate, they're space-like separated. You're just using this background to extract this entanglement, right? So how does entanglement harvesting typically go? You basically pick 2 probes. They can be atoms, superconducting qubits, something. You couple them to the field of space-like separated regions, so the interaction regions have to last for finite times, so they cannot communicate. And you'll find the parameters that allow probes to harvest entanglement from the field. So this is what a typical entanglement harvesting plot looks like. So this is the negativity of the 2 detectors in blue as a function of their energy gap. And then what you will see will be, well, there are some energy gaps for which the detector can harvest entanglement. Ignore the yellow line here. Marco is going to mention more about this. But it's just a small number, usually, right? Typically very small. What happened to the infinite vacuum entanglement in QFT, right? So it's never been measured, as a matter of fact. So just to advertise the next talk by Marcus here, Marcus will mention how basically we really improved this by playing with the time profile of the interaction, so the shape of the interaction regions in time. But again, Marcus will mention more about this, so just move forward. But the idea is that, and also we have another talk later about using many detectors to basically get a super additivity of entanglement when you use multiple probes. So good, this is the progress in entanglement harvesting and optimizing. You'll hear more about this soon. And finally, oh, sorry, there's a summary. Sure, they can access these local field degrees of freedom. They can extract entanglement from independent regions, and entanglement harvesting has not yet been done experimentally. So the nice thing, the experimental thing, is how to basically implement some sort of entanglement harvesting, not extracting entanglement from the vacuum of a fundamental field, but extracting entanglement from two causally disconnected regions, or from two regions that effectively cannot communicate of a BEC, of a Bose-Einstein condensate. So this work in collaboration with Francesco and Markus Oberthaler. Markus is a very, big name in cold atom physics and Bose-Einstein condensates. So very nice to be working with him. He's super interested in this. He really wants to implement this experiment, which is very exciting. So what's the idea here? So when you have many bosonic atoms, very cold, they condense into the state that is effectively described by one single state. And the density fluctuations of this, or the density of this state, if you consider fluctuations around a given classical background that this BEC will be at, then what happens is that these fluctuations behave exactly like a relativistic scalar field in a spacetime, where basically the speed of light in the spacetime is actually given by the speed of sound in the Bose-Einstein condensate. So basically, you get your standard mode expansion for your delta rho b, and the little asterisk here for the exactly, it's because this is actually the momentum of a real scalar field. Good. So what's the idea then to locally probe this? You can place an atom of a different species compared to the condensate inside this BEC. You can trap this with a dipolar trap, and basically you get this dipolar potential, and you drop your atom there. You get different energy levels there, and now what can happen is basically that you can just place this inside the BEC. If you do this, now you have something that is interacting with the BEC. The problem is that this interaction between the two, so it's like it's always switched on. It's an interaction which is the density of the BEC and the density of this polaron, which is basically this wave function of the excited and ground state, right? So this is not controlled in time yet, but what happens here is that this interaction is proportional to this scattering length between the two, which is an effective parameter that basically controls the whole interaction. And if you just expand this interaction, you do get exactly, or basically exactly, a two-level under the width detector interaction with this relativistic quantum field. But the problem is we still don't have the time control. We only have this spatial localization given by the wave function of the ground and excited states. So how do we implement the time localization? It turns out that the scattering length, it depends on whether there's a magnetic field applied to the system or not. So if you put this whole system, if you apply a magnetic field to the whole system, what happens here is, this is, for instance, what the scattering length looks like as a function of the applied magnetic field. As you can see, there's a zero, right? It crosses zero, effectively. So what happens is, you start your magnetic field at this value such that there is no interaction between the two. And then what you do is, well, you tune it a little bit, and then you put it back. What you just did is you implemented a finite time interaction. They weren't interacting before, they interacted for this pulse, and now they're not interacting again, right? So the idea is basically implemented this, the final, so we implemented a switching function, as we call it, right? And the f of x is just given by the wave functions. So you have this finite interaction in space-time, given by the product of the two, that localize the interaction both in space and in time. And you might notice that basically, instead of having the speed of light, we have the CS, which is the speed of sound in the condensate. Good. So Markus wanted to have a picture for the paper, so he hired someone to do this picture. Let me just, the person used AI anyway, so I don't understand the point. But okay, still, the point is, this is a pictorial illustration here, but important. This light cone, which defines the region where the polaron sees the BEC, is defined with respect to the speed of sound of this background. And this 2 + 1D is just for illustration purposes. You can do this in a 3 + 1 effective BEC. Cool. So basically, to do entanglement harvesting, you have one of these, you put the second one, well, you find the parameters, and you find whether they harvest or not, right? So this is basically the actual region parameters that we were using before. This might have to change soon, but it's okay. It's a good approximation. But then you place these two polarons in a BC, do the switch on and off of the external magnetic field, or around this 0 value for the scattering length. You create this magnetic pulse for finite time. Then you make the separations between the detectors larger than their interaction time, so that effectively they cannot communicate through the BC. And what you find is parameters, and to try to find parameters such that there might be entanglement between the probes. So basically here it's as a function of this internal energy difference between the two levels of the impurity in the dipolar trap. You can find negativities of the order of 10 to the minus 4. There's something important about this plot. You see this? You see this? These are units. These are actual numbers. It can be done in experiments. This is not 1 times 10 to the minus 4 times lambda squared, where lambda is a perturbative parameter. This is 1 times 10 to the minus 4, which is measurable according to Marcos. So the numbers are fairly optimistic. Good. So conclusions. Correlations in QFT contain this information that cannot really be seen in long-time regions in the sense of entanglement and things like this. You can find these most entangled modes between two regions in the vacuum. And finite time interactions sample these local properties of the field, as Marcos and Sebastian will mention some applications during their next two talks. And finally, we'll be able to measure vacuum entanglement in Bose-Einstein condensates very soon. But not only that, anything that can be done with unreadable detectors. Measuring correlations, measuring vacuum excitation, all of these things can be done with a setup like this, because we have a detector that couples for finite times. So with that, thank you so much. And I've completely chewed my question time, so probably I have time for half a question.
Thank you, Rick. If there is a very quick question, you can take it. If not, then
we're on schedule. That's good.
Let's thank Rick again. And the next speaker will be Marcos Morote Balboa, who will tell us about optimization of entanglement harvesting with arbitrary temporal profiles.
Cool. Just set a timer. Okay, you tell me. Okay, cool. Well, first of all, thank you for the invitation. As Rick mentioned, I'm going to be talking about the optimization of this protocol that he just explained, in particular how to tune the shape of the interaction region. So in this talk, I'm going to start by saying just a few words on entanglement harvesting, just to summarize what Rick just said. Then I will explain how we're able to do computations in entanglement harvesting for this arbitrary parameter that we're going to optimize over. I will show the results that we got when doing this optimization. And finally, I will show why these results leave second-order perturbation theory. So, just a quick summary, as Rick explained, in entanglement harvesting, we typically have two unrootable detectors that interact in two regions of a quantum field that are usually called capital lambda A and B. And it can be shown that to lead in order in the perturbation constant, the entanglement between the detectors after this interaction, which is given by the negativity, depends on two things. The non-local smeared Feynman propagator, which basically encodes the non-local quantum correlations between the two regions, and the local smeared Weismann function, which encodes the noise at each detector. It's basically the excitation probability of a single detector. Now, let me seize on the fact that we usually take these regions to be space-like separated, and that is because this negativity is only telling us whether there is entanglement or not, but it's not informing us about the origin of this entanglement. Because sure, the entanglement could come from this genuine harvesting from the field, but entanglement can also come from signaling. Say, for example, they take space-time regions that are defined by Gaussian functions, just like this. Well, of course, Gaussians are not compactly supported, and so these regions are not compactly supported regions. these Gaussians are always going to have some tails that are going to leak out of this compact support region. These tails are going to propagate, and to some extent they will cause some signaling. Therefore, we need a way to be able to quantify this signaling, to know how much of our entanglement comes from communication. And the way that one does that usually is to split the Feynman propagator in two parts. This H part that we call the Hadamard function and just encodes the state dependence, and the important part for us, this delta or symmetric propagator, which encodes the communication or signaling or causal connection, whatever you want to call it. Now, let me give an example, which is what we'll compare our results to, and it's precisely with these Gaussian functions. So say that you have these two interaction regions given by Gaussian functions, and you place them separate enough such that your communication is negligible with respect to the negativity. As Rick showed, you get these sort of plots, these entanglement harvesting plots, which tells us two things. For one, the fact that there is a non-zero negativity tells us that there is indeed entanglement between the detectors. But more importantly, and this is something that Rick didn't mention, is that this orange curve here, this delta, this signaling, tells us that most of this negativity came from genuine harvesting, because at the peak of the negativity, this signal is only of about 5%. So there we can conclude that entanglement was genuinely harvested. And this is great, because this tells us that in this setup, we can genuinely harvest entanglement. The issue with setups of this sort, as Rick mentioned, is that the values of the negativities that we usually get are too small for experimental implementations. And this is precisely what motivates this work that we've been doing now, optimizing the protocol. Now, there are different parameters over which one could optimize the protocol. The one that we chose, which we thought to be one of the central ones and often overlooked, is the actual shape of the interaction. In particular, we focused on just the shape in time, the switching function, but it can be extended to the whole space-time shape. And this is something that is often overlooked because, well, even just finding a function that allows for entanglement harvesting is far from being a trivial task, so let alone optimize over it. The way we're able to do this is the simple idea, which is just to take bases of L2 functions. We consider truncated bases up to a certain truncation n of Hermite functions, and if you do that, well, you can write any switching function, any spatial shape in these bases. Nothing new here. Now, let me also mention that these functions, these basing functions, depend on this Tn, this parameter that depends on the truncation, which even, well, I'll speak about it later, but it will basically allow us to make sure that these functions that we consider remain effectively compactly supported to avoid this whole tails thing. So if you expand your switching function in these bases, it can be shown that computing propagators is no longer a multidimensional complex integral, for which you usually don't even have closed form expressions, but you can simply write it as a matrix product, where this matrix here is just something for which we got closed forms through generating functions, and these vectors are just the components of the switching functions that we use for smearing in these Hermite bases. So if we do that and we impose some more constraints to, well, be able to compare with the Gaussian case, as I mentioned, the negativity for a given switching function can now be simply computed as two matrix products. And this is something easy. It's so simple. It's so easy that we indeed develop a very simple website where you can go scanning the QR code or following the link, and it allows you to do just that. You can choose a switching function from a family, or actually go in and tap it in, and you can get these sort of plots, like the one that Rick showed, in fractions of a second, and download the data and play with it. But another important aspect of this whole matrix formulation of entanglement harvesting is that this becomes a simple eigenvalue problem. And so maximizing the negativity can be recasted as finding the largest eigenvalue of a certain matrix. Now, this is precisely what we did during the optimization in 3 different cases. The first case we consider space-like separated regions. And yeah, as I said, we will always have some tails that are going to propagate and such, but as I mentioned, we can approximate space-like separation by playing with that parameter Tn that we had in the Hermite functions. Indeed, say that you didn't have that parameter, well, if you consider Hermite polynomials with larger and larger n, they're going to leak out of your region, and you're going to have the same issue with the tails. But if you implement this parameter, then you can consider larger and larger n's, and you will always remain effectively supported within that region. So that's how we are able to implement this setup, where regions are effectively separated, space-like separated. Now, if we do that, we can do this thing that I mentioned of taking the largest eigenvalues, and we get this. Now, this is somewhat similar to the plot that Rick showed, but it goes even further. Here we're now taking we're not showing the negativity of a function. We're taking for each subspace of functions, of Hermite functions up to order n, and for each value of the energy gap, we find the function that gives the largest negativity. So for example, at this peak here, we have the best Hermite function, the best switching function within the Hermite functions of 200 terms that gives the largest negativity at omega t0 equals 10. And by doing that, we can then already see that just within this setup, we can get negativities that are 1 order of magnitude over what we get in the Gaussian case. But we can go even further, because if we look at the actual functions that give us this shape, we can see that they become more and more oscillatory, which is very interesting because if we take the largest value over these omegas and we plot it, we can see that this negativity, this largest negativity, seems to diverge, which agrees with the claims made by Resnick in this 2005 paper, where he claimed that the negativity of super-oscillating functions diverged with a number of oscillations. But this is not everything. The second case we considered, we didn't have space-like separation anymore. We allowed for a little bit of interaction between the detectors. Now, this is mainly because by allowing more time, and the detectors can probe the field for longer times, we expect to increase the negativity at the price of having some communications, but we argue that this is fine as long as it remains reasonable. So around 5% like we had in the Gaussian case that we're comparing to. In that case, we're able to find negativities of 10 to the minus 4 while keeping a signaling of around the same as the Gaussian, which is now 2 orders of magnitude on top. Now, in the last case, probably the most interesting one, is when we have something more like this. We have two detectors that are now causally connected. They are fully able to communicate. But we show that there are very specific values of the parameters for which this communication is exactly 0. Indeed, you can see that for most values of this energy gap, the signaling, the orange curve, is extremely large and overtakes completely the negativity, which is mostly 0. But for a very specific value, this signaling changes sign and it's exactly 0. And in this case, we can recover negativities of 10 to the minus 1, 5 orders of magnitude on top of the Gaussian case. Now, what does this leave perturbation theory? Well, in second order perturbation theory, we're considering that the next order terms, in this case the propagator square, do not contribute to the value of the negativity. So we neglect these second order terms, next order terms. The issue is that these largest negativities that we're seeing usually happen when the propagators acquire the same value. And so the negativity, which is given by the difference, is usually 1 order of magnitude smaller. So what does everything look like? Well, in the Gaussian case, where we had negativity of 10 to the minus 6, everything's fine. We had 10 to the minus 10 for the next order terms. These are definitely can be neglected. So there we're still within perturbation theory. As we progress within the other scenarios that we consider, things got perhaps slightly worse. We're closer to the edge, but we're still well within perturbation theory. Maybe in the second case that I mentioned, we had 10 to the minus 4 for the negativity and 10 to the minus 6 for the next order terms. But as we reach negativities of 10 to the minus 2, we can see that our next order terms are already of the same order of magnitude. There we cannot neglect them anymore, and we cannot claim to remain within perturbation theory. But if you remember for the last example, the case where we had this causal connection, we got negativities that were even larger, so fully outside of perturbation theory. But of course, this is not all, and things get even worse. In the Gaussian case, where we didn't have any optimization or whatsoever, again, we had 10 to the minus 6. This is our baseline example. Now, Rick mentioned in the other paper that by switching to this momentum coupling and by actually using things with units and so on, they were able to recover 2 orders of magnitude on top. Now, in this work, we gained 5 orders of magnitude while remaining in the field coupling, and we showed that that already leaves second-order perturbation theory. So, well, one can only wonder what would happen if we performed the same exact optimization when considering coupling to the momentum. Now, I don't want to make any strong claims, but we believe that this might hint at the fact that we may need to consider new ways of tackling entanglement harvesting in the future. And with that, thank you again for the time.
Thank you, Marcos. We have time for a few questions, if there are any. Yes.
Is there a clear intuition why you get the negativity going to infinity as you take the oscillatory modes to become more and more oscillatory? Is this the UV behavior showing up or something else?
Well, there's a good question. I think the way we thought about it is that as you have more and more oscillations, which is what Resnick claims, you're going to probe higher energy modes of the field. And that is the reason why, well, I mean, of course, this is all within this lambda square, what is going to diverge. But I would say that's the reason.
Can I ask something else?
Yeah, sure.
A quick question is, I mean, Rick started his talk about referring to this paper by Srenicki, where basically computes the entanglement between some area and the complement. What happens if you take the limit in your case and you do that? Like, is there a way that you can think about the detector and another detector that's completely spread out and everything else, and do you recover something? I literally mean, like, because you're basically computing entanglement between different regions, right?
Mm-hmm.
But if you now use all of that machinery for the region and complement of the region, do you have any intuition what happens?
It's a very good question, and we hadn't thought of it. We're now trying to use this machinery, as you called it, for this work that Rick is doing with Patricia, for the most entangled modes, not in entanglement harvesting, but literally within the quantum field. I don't feel comfortable making claims about it now, but it's a very interesting question. Yeah, we should definitely think about it.
Absolutely, because to try to do something like entanglement harvesting in that case, you would need to have a detector that basically pulls to everything outside of a given region, right? So it would be a very, I don't know, not really delocalized, but like kind of, I don't know. It would be a detector with a hole in the middle, right? And a very large detector with a hole in the middle. In this hole, you put another detector interacting for finite times. And I'm not aware of anyone that has tried to do anything like that. But I would expect that, I mean, in some cases, yes, like in the area loss things, like there are some people that relate these things with detectors. But I would expect that you'd be able to see way more entanglement if you were able to produce this probe. Or even, hopefully, we're going to have a later talk today that uses many detectors. So one could consider like entanglement between one detector and many other that are around it or something like this. But definitely not within the formulas of having 2 localized probes, right?
Right, let's thank Marcos again. And the next speaker will be Sebastian Holmén with a talk on non-perturbatively extracting the 2-point function of a relativistic quantum field.
Oh yeah. Right. Where is the cable? Here. Right. Right. All right. Hello, everybody. Thanks for letting me talk here to the organizers. My name is Sebastian Holmén. I'm a last year master's student at the Stockholm University in the master's program in theoretical physics. And I'm working on my master's project right now with Rick Perche as my supervisor. Part of this project has been writing this paper called Non-Perturbative Measurements of Two-Point Functions in Quantum Field Theory. What we tried to ask was basically, could we couple local probes to a field in sufficiently many regions and find the right sort of measurements to perform on these local probes, such that we could extract the two-point function for the field. And we recently put this out on the archive, so you can find it there. Okay, so how does this work?
Have you connected it to your computer?
Oh no, I have not. Let's just do it like this then. Okay, so I will start by talking about the state. Rick already mentioned some of this, but so we think of the state as a linear functional omega that maps our algebra of observables to numbers. Okay, and it has to be normalized and it has to satisfy the positivity. And this is very analogous to density operators in ordinary quantum mechanics, where the state is just something that maps our observables A to some numbers. And it also has to be normalized and positive. So to know the state, we really need to know how to map all of these observables. And that is quite hard to know, because there's usually a lot of observables that we have to think about. And these are encoded in the endpoint functions, as we call them. But fortunately, there is a class of states where the two-point function is enough. And these states are the quasi-free states. These are zero-mean Gaussian states. So basically, we only need to care for this two-point function that sort of measures the field correlation. The field here is phi. It's correlations between these 2 points. And all the odd points functions vanish, and all the even point functions can be described in terms of this one. So if we know this, then we know the field. That is basically what we're trying to do. So we can break it up into a symmetric and an anti-symmetric part. This anti-symmetric part is the anti-symmetric propagator. It's totally geometry dependent, so it is completely determined by our equations of motion. So this thing is known. So then all the state dependence is hidden here in this H, which we call the Hadamard function. So what we set out to do was try to find a way to extract this from the field such that we can know the two-point function. Yeah, how do we determine it? Okay, so we need to locally probe field, as Rick talked about earlier too. So we sort of have to couple something to the field, where we then can make measurements on this thing we couple to the fields, and these things are our local probes. Yeah, so then we do not get the these distributions between points, but we rather get them averaged over the regions we couple to. So here we will describe the regions with these lambdas xi and xj, which are some regions sort of centered on the xi and xj. Important to remember that we get these smeared distributions. Yeah, smearing regions, and yeah. So what do we use to probe them? So introducing the unrooted width detectors again. So these are just some two-level system. It couples to the field in some defined region of space-time. Here I try to illustrate this with, this is some path through space-time that our detector is taking. And here is the region where it couples to the field. This could be like a qubit, for example. We will have this interaction Hamiltonian. So phi here is the field. Lambda here is this smearing region I tried to show here. And this is smearing region in space and time. Very important. The small lambda here is our coupling constant, but as we will see, this will not be very important. So here, this is the monopole moment, mu here. And note here that there is no energy gap. Maybe you recall from Rick's talk that there was some exponentials there containing a omega, the energy gap. But we take this energy gap to be 0. And this has some advantages. For one thing is that our time evolution operator becomes much simpler to handle. You see here that it takes the this interaction Hamiltonian. as an argument. So yeah, we can determine this completely analytically, which means that to get our final states, we can just perform a Magnus expansion on these exponentials. And then we get analytical solutions for the final states of the detectors after they interact with the field. Yeah, and unlike previous methods, we are not limited to the perturbative regime here, because if you have this energy gap, then you have to assume that lambda is quite small. Yeah, so now we have one detector that couples to the field, and we can extract information from it. But we need multiple regions to get the correlations between. So we introduce these sequentially coupled UDW detectors. So now, instead of just having one qubit per detector, now each detector carry many qubits, and then they interact in their own regions here sequentially. So now we just have to modify the interaction Hamiltonian a little bit. So we just take the sum of all these interactions, essentially. So now we have stored some information from the field in all these places, or in all these qubits that we then can perform operations on. So, but these are only causally connected, because this is a detector undergoing some trajectory. But we also want to consider causally disconnected regions. So we use multiple of these detectors. So here we just put a lot of them in here, and now we have this lattice of interaction regions. So now, this was one of the things we wanted to do. We wanted to find these interaction regions. So now, what we will try to do is sort of find what operations we can perform on our UDW detectors, such that we can the measurements we can perform, such that we extract the Hadamard function from this. So that is what we will do here. So just some notation. So these are our expected values with these have been the sigma matrices acting on detector labeled I and J. And alpha and beta just tell us what sigma matrix we are acting with. So what we are doing and where we are doing it, essentially. Then this was sort of the main goal of the paper. So we found that this smeared Hadamard function between regions I and J is given by just taking the ratio of these expected values. So this was quite simple, actually. So now we have this in closed form. Now, for arbitrary separation, we can have this time separation, and now there can be some like causal influence from the regions on each other. So this is this Cij term that we have to sort of remove in order to just get the interaction, the Hadamard function between these two regions I and J. And this was also like possible to get in this quite nice form. So we just sum over all the like uninteresting detectors, or the detectors we are not concerned with at the moment, and just like sort of remove all this causal corrections. I have to mention something that is that this is all in general spacetimes. Everything up until the examples will be in general spacetimes. It's very important. So this is very, very general. Yeah, exactly. So like this was what we set out to do, and we have actually done this. So one could imagine like somebody like actually like creating this lattice and doing all these measurements and finding these expected values, and then they would actually know the Hadamard function for the state. But yeah, physical probes are not point-like. So we have some regions that we couple to, but to know the state, really, we have to know the point-like Weitman function, or the Weitman function between these events. But we only have these averages. So yeah, these are not the same thing, really. Yeah, so we decided to try to estimate this error through a multiple expansion. So to do this, we needed to choose some kind of smearing regions. So these are space-time Gaussians centered at the event xi with characteristic size L. So yeah, in both space and time, these are spread out. Right. And we did this in Riemann normal coordinates, since we are doing this in general spacetimes. So what we found was for these smearing regions, the largest order corrections are only of L squared, which sort of makes sense because then we imagine that as we make these detectors smaller, we would like approach this. And in fact, like these smearing regions approach space-time deltas as L go to 0. So then we would really expect to this to become 0 and this to be equal. So we did some examples of this for different states. So the simplest one was the Minkowski vacuum. So here we have detectors on the the positive side here. The detectors are only separated in space, and here they are only separated in time. In both cases we call the space-time distance S. So what we did was we plotted the two-point function between events, the thing we are sort of trying to get, a smeared two-point function, and our multiple approximation of it. And we plotted this against the separation ratio with the size. So as we see, as the separation becomes very large compared to the sizes, we sort of approach a point-like case. And indeed, our approximations become very good when this ratio becomes very large. We also did a thermostat. The approximation is still here good, but I think I'm running out of time, so I will just whiz through this. We did a coherent state also, and we did a one-particle case, which was the most exciting one. But let's get to... Yeah, I can just briefly mention that this is the background Minkowski. The Minkowski vacuum is this blue thing, and this red thing here is with the addition of the one-particle state sitting in the space-time. And once again, our approximation captures this, this extra dependence on the one-particle state. Okay, so what improvements have we made on previous methods? And mainly methods that did use gapped detectors. Okay, so our results are non-perturbative. So we can use any coupling strength we would like. Yeah, and the limit for where the interaction regions become very small, our functions are regular. This is not the case if you have gapped detectors. And also for gapped detectors, you get an imaginary dependence on the energy gap when you go into this limit. But since the energy gap is 0 here, we do not have this dependence. And finally, we have shown how much the interaction region actually makes our recovery diverge from the point-like case. So that was everything for me, and thank you for listening, and I will be taking questions if I have time.
Thank you, Sebastian. We have time for a few questions, if there are any.
Thank you for the talk. Could you comment a little bit more on how you do this non-perturbative evolution?
This non-perturbative evolution, over here?
Yes.
Yeah, so basically it's just like the ordinary thing we do in time evolution, where we just take our our initial state and just sort of sandwich it between these time evolution operators, and then just basically calculate what we end up with in the end.
So you don't do Dyson expansion there? You manage to compute all orders of that exponential, or?
Yeah, so we did a Magnus expansion.
Okay.
That was basically it. So we expand it in terms of, correct me if I'm wrong, but in the terms of the, what do you call them? The
commutator?
The commutators, yeah. And the thing is that this thing will become independent of the time, because here this is independent of time. So the higher orders of the commutators will vanish. So it becomes very short, this expansion. So it's cuts off at the second.
So okay, I see. You can sum them up because of that. Okay.
Are you familiar with the Magdalena Zych question?
Yes. I did not get that point. So.
Right.
Any more questions? I don't see any. Then let's thank Sebastian again. So this was the last talk before lunch. Now we have lunch break and we'll be back at 1.
Yeah. So for lunch.
Right, welcome back. So now we're here for the career development talk. So we've got Magdalena Zych and Guilherme Franzmann, who are academics here at Stockholm University. So it's just going to function kind of like a discussion about career opportunities in Stockholm and your own experience and advice for young people in this field. So the first question is, so what are the current open positions in the Institute? What is the application process, and are there any recommendations that one should take into account when writing the application?
So I guess maybe I'll speak for Physicum, and then you can cover Nordita. So for Physicum, there are no departmental PhD positions. And of course, postdoctoral positions are also typically not directly, I mean, some universities have their own PhD postdoc program. That's also not the case. So essentially for any open positions, one has to check the website for open calls. And these are essentially positions that individual researchers open from their grants. So there isn't any particular season, maybe grant one can see when there are major grants like VR and so on, and people might be opening. But otherwise, one has to essentially regularly monitor the page, and the application process is the usual documents that needs to be submitted. But then you have to keep in mind that it's individual researcher that opens position, so the advice here is read very, very carefully what is the context, if there is any grant that funds this, then try to learn about what this grant is aimed to deliver and what's written in the call. You can always contact people for some extra information and really seriously engage with this when you apply, because that's going to be the main criterion then.
Mm-hmm.
I guess I can talk on behalf of Nordita. So for people that do not know, Nordita doesn't deliver degrees. So if you want to do a PhD or a master degree, you need to actually be associated with Stockholm University or KTH, even though academics working in Nordita can supervise PhD students, master students, and also postdocs. Similarly to Physicum, mostly in the last few years, to actually get to Nordita, you need to come with your own money. There are current positions that were open, and there are going to be more positions in the future. But more easily, you might try to actually consider checking out different fellowships you can apply for. And there are some Swedish fellowships that people might not be aware of, and they're always free to contact me or Magdalena or people Physicum Nordita if they want some tips of how to get to know those different fellowships or grants, that they are not that famous, and if you're not a local, you might not be aware of them. And maybe...
Yeah, I think that's something we could talk about. That's something we could talk about separately, so we can take it as an extra question in case and go through some of the options.
And maybe a quick remark also back to the question and what Magdalena said. If you do not want to be refreshing some page every now and then to see if there are positions, nowadays you can actually use Cloud Cowork or Codex to have an automated script that search you for positions on a weekly basis and send you a report. So you can actually also look into that.
Yep. So are there any, following on from that, I suppose, given that you need your own money to come to Nordita, what kind of grants are available to come to Stockholm then?
I mean, the ones that I just mentioned, in particular, there are two that different people, including people who are here, have at the moment, and my own grant is coming from one of those foundations. It's called Old Enquist Foundation. There you can apply for grants of different sizes, all the way to actually being able to fund your full equivalent of assistant professor position. And then there's another foundation called Van der Green Foundation that also has fellowships that are meant to bring foreign researchers to Sweden. There is discussions in different departments at the moment concerning the nature of those grants, because some of them are tax-free grants. But at the moment, at least through the universities that we have around here, meaning KTH and SU, you can still actually have those stipend tax-free fellowships.
I mean, maybe I'll add for context because it might sound fantastic, tax-free. We all want to take it, but the caveat is that there is no social insurance, there is no loading for pension, and yeah. So if that's something that one cares strongly about, and especially if somebody comes from outside Europe, the social insurance aspect might maybe be something more sensitive. So yeah, it's not just a bonus that you don't have to file the tax. There are these these caveats.
Yeah. Okay.
But then maybe we did not mention VR, Swedish Research Council, that also has some fellowships. So I've been flicking some
group leaders.
VR stands for Vetenskapsrådet, and I'm sorry for my for butchering the Swedish word. So this is the Swedish Research Council. So they have various things, and maybe I'll just show those I thought are relevant for us here. International postdoc, where that's for people who did their PhD in Sweden. They do not have to be Swedes, but they need to have PhD from a Swedish institution. So this gives a so-called outgoing PhD fellowships, and then there are starting grants. As far as I know, you done your degree or any prior part of your career does not have to be in Sweden, but of course you apply to be based on in some Swedish institution. I think that's.
What about Marie Curie and all those kinds?
Yeah, so since I guess we focus more on the opportunities that are somehow funded by by Krone, so we did not mention, but yeah, there are international schemes like Marie Curie and probably many more that we are not aware that could allow people to go from anywhere to anywhere, but at least they are not included in this list. Maybe we can include some information on this, if there is any global RQI that is not like fully delocalized, not associated with any node. We could consider collating such information for that, so we don't lose those. Yeah, if we want to compile a list. Yeah, I think.
Yep. Yep. Okay. What are the current career prospects? What are the career prospects for current researchers in the institution and future researchers in terms of where they typically go after coming to Stockholm?
A good question.
Can you repeat the question?
What are the career prospects for junior academics that come to Stockholm after they finish their studies or postdoctoral work here?
Yeah,
what do they typically?
Yeah, at least I didn't do any proper statistics, so it would be hard to say something that is really based on some unbiased numbers. But at least in terms of quantum theory at Physicum, there were a number of people in other groups who finished their PhDs, and they went to do postdocs, or postdocs that moved through the group, through various groups there and moved on to postdocs, and these are places that I don't know include ETH Zurich, places in the US, Finland. So people find positions. I think the question is like, what is the prospect of say coming for a postdoc and staying on a permanent position? That doesn't seem to be the main path. I think, in case we can ask Sofia how you do it. I think she's the only example I know. But obviously, one needs to apply for an open position and get the position. So that seems to be not a very surprising path. But let's say there isn't, to the best of my knowledge, there isn't any proactive. There isn't any initiative proactive to keep excellent people that come. So if a prefect can go and speak to the rector, if there is an excellent researcher, I think there will be like their initiative, and maybe there is something that can be done, but certainly it's not something that people have in mind. Okay, we should have some strategic pool of money if we get someone really outstanding to keep them. I don't know about something like this. I think on the level of university, I think the financial buffer is there, so it's perhaps up to then the groups to pitch to the department heads to pitch to the rector, but it's not some. Yeah, it's there is no precedence as far as I know.
Yeah, right. I suppose many of us who are still here are the first generation of this field. Yeah.
Yeah. Okay. Then maybe since I didn't mention in this list the funding that I have here. So this is Wallenberg. It comes from the Knut and Alice Wallenberg Foundation, and they fund the Wallenberg Academy Fellowships. So these are positions that at least Stockholm University gives you. So it's a fellowship, but Stockholm University gives you permanent position if you get one of those. The process for this, though, is there is a lot of gatekeeping going on. So first you have to be nominated at the department, then at the faculty, then at the university. Then you can actually apply to the foundation. Since the faculty and the department, they commit some money because they commit to hire somebody permanently. In the last round, the Department of Physics actually decided we will not be nominating anyone because we do not have the funding. So it's not clear. I don't think that the department will never consider, but since usually there are very strong applications in each round, there is someone getting this position. And therefore, it's in a sense a risk, financial risk for them that, okay, they will get someone who will be selected by the foundation, and then they have another permanent position to fund. But if they will consider, then I would say this is one of the options where whatever research topic you do can be very foundational. You then have a chance, like you are not bound to whatever departments consider to be like particularly strategic at the moment.
Maybe a quick comment is that, unfortunately, the same reason why that happened is that at the moment, if you apply or if you come to Stockholm with an ERC, since last year, you do not have that position as a tenure track position anymore. And so for the remaining future, I think the situation won't change, as far as I know, until maybe 2030 or afterwards.
It's a long time. Yeah.
Yeah, I mean, maybe not to paint a picture of some completely bankrupt department. I mean, there is some financial problem, but it's because during the time of rapid growth of prices and inflation, the government increased salaries for government employees. That includes researchers, but they have not increased the funding that goes to the universities. So like grant income and so on, it's not like people suddenly are doing particularly worse. It's just the department, the universities have to shell out more money for the salaries from more or less the same budget. So yeah, in proportion more.
How is the salary and benefits in Stockholm compared to the cost of living in Sweden?
So I can give some numbers now in terms of cost of living. Perhaps we can also get some testimonies from the audience. So just scrolling. So PhD positions, the median is now 32,500. This you start with a little lower salary at the beginning, and then once you are past your half-time review, it gets increased, and then once you have done 80% of requirements, and it gets again increased. So yeah, maybe some PhD students can say like, is this reasonable? How much of that would go for rent? I don't know if anybody would like to speak up.
Ask a question? Is this before or after tax?
I think
it's 32,500
before. So you need to give back a third of it probably. Yeah.
So it's a quite decent salary compared to the cost of living. There are options for very affordable student accommodation, which you can get for sure for less than 10,000 crowns.
I mean, you can get student studios that would normally in the city cost 2 or 3 times as much for about a third the price, is it?
Yes,
Yeah.
yes. So I would say it's a very good salary for a PhD position. Definitely enough for one person. Sometimes it's enough for 2.
Yeah, then maybe I can mention current. If you are doing the numbers, I've pulled out, I think, official number that it's given for the postdoc salary. When people need to estimate how much they spend on the grant, is 42,800 or maybe 500. All these salaries are increased yearly by some small percentage. So yeah, let's say if somebody looks next year, that can be slightly different amount, but it just gives some ballpark number.
Yeah. How do the different RQI groups, related groups, collaborate in the institution, and how much ongoing, or how much does that happen? Or
Should we comment on that, or we pass to the audience? Yeah, we can comment. I think I don't know if there was we didn't maybe have an overview of the RQI groups, but so maybe just we can mention some names. So. Well, we are obviously interested in the RQI topics and people in our groups as well. Then we have Rick with his students. We have Sofia with her group that are doing some RQI research and some things maybe that are more broad, but I would still count as RQI friends at least. And Fabio Costa, who also would definitely count as doing RQI research. So the I'm not sure.
She's doing a lot of quantum information.
Yeah.
I would say that it's I mean that's 2/3 of RQI, right?
Yeah. Yeah. Yeah, and then I think in this configuration there are collaborations. So we have collaboration with Sofia, with Rick, and hopefully growing in strength. Fabio as well. So there is a lot of already trodden paths, and also a lot of interactions, even if not direct collaboration. There are, especially for junior people, there are a lot of scientific events that people can attend, and I think the environment is supportive of people developing also independently collaboration, reaching out to colleagues they think they might have expertise or maybe they are interested in the topic and working with them.
Yeah, I think that should wrap it up. So we should move on to the next session now. But thank you for all the questions.
Thank you.
Yeah.
And then there's the HDMI marking, I guess, this one? Okay, thank you. I will clip it on like that, maybe. See if I manage. I'm going to be touching the microphone a lot, I'm sorry.
Okay. Next up we have Sofia Qvarfort, who's going to speak to us about her research on sensing gravitational acceleration with large mass quantum resonators. Thank you.
Thank you, Germain, and thank you, Jerzy, also for organizing this today. It's very nice to be here. It's very nice to see people and some new faces as well. So I was also at the previous RQI circuit 3 years ago, and this is basically the same talk, because since then I got distracted by more quantum information side of the RQI one, which is still included, which is nice. But today I'll tell you about research we have done previously on sensing gravitational acceleration with large mass quantum resonators. And I'm very happy to chat, to take any questions. I'm very short-sighted, so if you're waving, maybe wave more, and I'll try and spot you. So very quickly about me. So I grew up in Uppsala, which is just to the north of Stockholm. And the reason I got into physics was that I really love science fiction. And I thought physics is the closest we can get to actual science fiction. But then I thought Sweden was a bit small, so I moved to the UK to study. So I did physics and then also stayed on for a PhD. And then because London is a really big city, you can essentially keep hopping between the universities. So I went from UCL, where I did the PhD, back to Imperial, also for a postdoc. And then at Imperial, I did the undergraduate as well. And speaking of PhD salaries and so on, I'm very happy to talk about moving to the UK and so on. Living in London on a PhD salary was not easy. I think it is easier in Stockholm, and I think it's gotten worse since. But London is a lot of fun, so spending your 20s in London was fantastic. But then in 2021 we moved back to Sweden, and I've been now shared between Nordita and Stockholm University. And then in 2024 got this assistant professor position, and have since then been trying to create a nice research space for people to talk and be creative in quantum physics and beyond. And this is the group that we have at the moment. So we call ourselves the Quantum Dynamics and Sensing Group. So we currently have 2 PhD students. Niklas is here, and then we have Max Goll as well. And then we have a postdoc who will be joining us in August. And then we are within the broader WINC context, which is called the Wellenberg Initiative for Networks and Quantum Information. And here we have some colleagues, including Fabio, who talked this morning. And in general, as Magdalena and Guy said, this context of Stockholm University and Nordita has been really fruitful for very nice collaborations and a lot of discussions going on here. Okay, so, but what I wanted to talk about today is quantum sensing, essentially, and then towards the gravity direction. And then to start very broadly, what is quantum sensing? Why do we care about it? So here we have the very basic setup is that we have a detector, we have a quantum system that is our probe, and we have some effect that we would like to measure. And why do we care about using quantum systems for sensing? It is because classically we are limited by this law of large numbers, essentially, where here the sensitivity of some effects on force, for example, is limited to 1/√n. And here n is the number of probes that we're using, so the number of photons, the number of atoms. If we now start adding quantum mechanics, we know that we can surpass this limit using, for example, squeeze states. So that is a resource that allows us to go beyond this classical limitation. Even beyond squeeze states, if we use non-Gaussian resources or even more, we can even go to some kind of n to the k limit. So this looks potentially very good if your k is large. But there are, of course, challenges. You can't do infinitely better than classical systems. So there are definitely questions that arise when you add decoherence and so on. So to talk a little bit more, where does this quantum advantage come from? So for example, one of the resources we have is entanglement. One of them is access to nonlinearity. So that is, for example, when you have self-interactions between a bosonic mode and itself. So for example, if you have the number operator, you would have the number operator squared. That would be an example of a nonlinearity. And we know that we can have advantages due to this, but there are also some results which are a bit more depressing, which show that as soon as you add a little bit of decoherence, these advantages tend to go away. You either have to have very strong nonlinearity, or you have to use entanglement in a very clever way, or you have to actively error correct your system. So sensing is benefiting from influences from quantum computing and so on, which is quite exciting. But what is then the sort of modus operandi, what is the story of quantum technology? It is usually that we want some kind of encoding of our parameters. So say we want to measure theta, then we encode that into the quantum system using some process. So usually we just physically model what is happening. If you have a gravitational wave, does your system shake a little bit? Does it affect the light modes? We had some work there. Does it? What is it that happens to your system? And then the question is, what state in your system is sensitive to these effects? So if you have a state that is completely unchanged by the effect, then you can't measure it. So you need some asymmetry with respect to the incoming effect. And then finally, when you measure your system, which measurement is best? If this measurement can't detect a change, then you also are not really in the game. So these are the three main questions that you tend to focus on if you do quantum metrology as your main focus. And then we have this is what the experimentalists care about, in the sense that if you have a signal and then if you have noise, you need to be able to distinguish your signal from your noise. But on the theory side, how do we quantify this? So we care about something called the Fisher information. So this is a geometric measure of how much information you can get out of the quantum system by measuring it. And we have here the classical Fisher information. I don't have much intuition to share for why it looks like this. It's something like the variance of the score of the maximum likelihood. It is a quantity from estimation theory. The important thing for us is that we get these probability distributions of the parameter given some measurement outcome x, with this modeling here, where this is a POVM that encodes the measurements that the experimentalist performs. And now this is in the classical case when you make a measurement. But what we can do now is to say, well, what if we optimize over all possible measurements and pick the best one? Then we arrive at something called the quantum Fisher information. And for pure states, it has this very nice, easy to calculate formula. As soon as you add mixedness or open dynamics, this becomes more difficult. But at least at this level, this is the best you can do. And this gives us a fundamental limit to how well we can estimate a parameter. So the Fisher information says that if you want to measure gravitational acceleration or this gravitational wave parameter, then you can't do better than this quantity. So this already tells us where do we need to place the experiments in order to actually see something. And the reason we are also interested, this can make this link is perhaps more clear through what's known as the Cramer-Rao bound. So that says that the variance of your parameter, so you want this variance to be as small as possible, is lower bounded by the Fisher information. So now here, if we, and this curly m, here's the number of measurements you perform. So this always has this inverse linear scaling, but this can now scale, as we saw with this n to the k, it can scale much more interestingly with respect to the number of probes that you're using. And so, of course, here, if you now had infinite time and funding, you can make this very large, but often we don't. Often performing measurements on complicated quantum systems, we can usually perform a fair amount of them, but if you have to, say, cool your system or you have to do something beforehand, this already becomes really expensive. And what it also tells you is that if the Fisher information is 0, you can't possibly bound the variance. So this is a useful quantity in order to compute, in order to learn what you can measure. Okay, so then we come to the second part of this talk, which is these large mass quantum systems. So I really like this image he was taking in the UCL lab, not by me, by James Millen. And what you can see here is a levitated nanodiamond that is charged, and it's levitated, no, it's not a diamond, sorry, it's a silica sphere, and it's levitated against gravity in a Paul trap. So in this trap, you create this time-dependent electric field, and it spins around and creates a saddle point that holds the particle in space. And so this one we can see, you know, it's illuminated by a laser. It's probably not so much in a quantum state. These systems are very difficult to get to quantum states. But I like this picture because it's very beautiful. So why do we care about optomechanical systems? Well, we are motivated by their large masses and ways we can use them to test fundamental physics. So there have been these exciting ideas of can we detect gravitational entanglement, We also can use them to detect deviations from Newtonian gravity. I'll talk a little bit more about that in this talk. And we are also motivated by tests of quantum mechanics. So what about the measurement problem? Are there collapse theories that describe, that describe the dynamical collapse from a pure state into, or from a state into some measurement outcome? So these systems are also very good here. And we have this review paper if you are interested in what we try to collect all the ideas in the field up to, came out last year. So now I think there have been even more ideas since then. But if you're interested, we try to collect and focus minds here. Okay, so the key question then, to repeat again, is what if we have a very small, what if we have a quantum system that is one of these levitated systems, and now we put it in a superposition, what gravitational field will we see from this? We don't know. We don't have a theory that consistently describes this. There were some exciting results the other day, from a few years ago, where they were able to measure the gravitational field for milligram masses. And so you're trying generally to improve your sensitivity to these very small masses, but then you're also trying to make these masses bigger that you can actually put in quantum states. So you're trying to approach the problem from two directions. Okay. But in this talk, I wanted to talk about something adjacent, but also more practically applicable, which is just measuring gravitational acceleration. So beyond measuring the gravitational field from quantum systems, we can also construct things like gravity maps of the Earth. So this is taken with a satellite system in 2013, I believe. And here you can see these deviations from the mean gravitational field of the Earth. I think this is Hawaii. Which is kind of cool. And what is the use of this? So first, you can see a lot of geological features, but you can also track things like meltwater, which is really hard to do visually. We can also see that you can probe beneath things that you can't see. So, for example, they were able to measure these gravity deviations of Jupiter. You can't see beyond the cloud layer, but the core we know is solid. And the question is, what was it doing? And this is where these optomechanical systems come in. And when we have these large quantum systems, we want to interface them with something that you can use for readout. And this is just to show you a little bit what the different kinds look like. Here we have levitated silica spheres. We were cooled to the ground state a few years ago now. Here we have magnetically levitated spheres. Here we have drum membranes that were also cooled to the ground state. These were actually entangled, which is really cool. So we see that we are starting to see this quantum phenomena really on the, I will carefully say macroscopic level. People debate whether macroscopic level will come in, mesoscopic perhaps. And you have now more varieties of these systems. They come in very different families. People also couple these to qubits very nicely. And there's a lot of variety of what you can do. But as a theorist, it's very nice that most of these systems are described by essentially the same Hamiltonian. So now if we take one of the simplest examples, we have this moving end mirror on a cavity. And this is our mechanical element, which has a center of mass mode here. And it's coupled to light inside the cavity. And then it's on a spring here. And if we look at very small displacement of the mirror, we can expand the system into this. So here you see you're coupling photon pressure to the center of mass position of the mirror. And usually this coupling here is time independent. We added time dependence here because it improved things a little bit on the sensitivity side of things. But now the question is, if we now have this system, how do we model this in the lab? How do we solve the dynamics? And how do we encode, if you remember what I said in the beginning, how do we encode these parameters that we want to measure in the system? And so the dynamics of this was solved in the 90s. It's given by these two nice papers. And it has a very simple form here. And it was also motivated by proposals for testing gravitational decoherence. So looking at if you take these very large mirrors, you put them in superpositions, what happens as they evolve, and can we detect loss of coherence due to gravity with these systems? But for our purposes of measuring gravitational acceleration, we now consider the case where we add a large object, Earth, for example, next to this system. We can then expand the Newtonian potential also for small displacement and add essentially a gravitational potential energy term, so mgx. So here x is then the position of the mirror. What we can also do is to consider an oscillating mass. So here we oscillate around some average position here. And this is generally easier to do in the laboratory because time-dependent signals, they stand out from this noise floor more explicitly. So the way we model this here then is that we now have a time-dependent constant here, which is a time-dependent shift, and then it's given by this here. So here you see that the mass of the quantum system plays a role. If you have now an atom instead of an optomechanical, like a large mass resonator system, this term is quite suppressed. To solve these systems, we use what's called a Lie algebra decoupling method. This is a way, because this kind of dynamics is non-Gaussian. Here you have 3 operators here. And that means that normal phase-space methods can't work. I won't go into the details of this, but if you're interested, very happy to chat about it. Here, one nice thing that this method lets you kind of see is that if you're given a Hamiltonian, can we actually solve the dynamics analytically or not? Do we have to use perturbation theory? And earlier today, we saw some very nice examples of solving things both perturbatively and exactly. The key sort of intuition behind this method is a little bit that you want to separate a notion of direction and speed for your quantum state. So your quantum state will evolve in state space like this. And if we can just isolate the directions and just solve for how quickly you go in each direction, then we can analytically solve the dynamics. But to then also jump to, so I won't show you how we do that here because it's just long calculations. And what we do then with that is to compute the Fisher information for measuring this little g. So here we have this quite horrible notation. There was not, it was quite difficult to find a good way to look at this. And at specific times, we find that this variance now of g is given by this very simple expression. So here is the mechanical frequency of the oscillator, is the number of measurements, is the mass of the oscillator, and here are some coupling constants and geometrical constants. Here you have the variance of the optics. So there you can see that having squeezed light is preferable to having a coherent state, for example. Just to show you some numbers, so if you now plug in numbers for experiments, so here we took things for a levitated silica system, you can see that the ultimate bound that you get for measuring gravity in this way is given by these numbers here. Which are comparable to what you can do nowadays with atom interferometry and these atom fountains. But in this case, we have not added noise, so the fact that the realistic systems achieve something like this is already very nice. For fun, we also included some numbers on if we wanted to measure gravitational waves. So if we want to get down to this 10 to the minus 21, what do we have to do? Well, we have to have a very long cavity. We have to have very high squeezing, lots of photons. These are not realistic numbers, but it was fun to see. I think I have 5 minutes left, so I will try very quickly to just say that you can also now insert modified gravity theories here. Oops, sorry about that. Those have jumped. Where you have a modified version of Newton's constant like this, or Newton's potential. These are known as, some of these are known as chameleon-like modifications, and what you usually try to do with these theories is that you try to bound them in terms of these free parameters. So these are the current bounds that people had at the time when we were writing this, and now I think they are probably better. And by using these techniques, we were able to say, look, if we have now optomechanical systems, they should also be able to bound these parameters in the ideal case like this. Here we also looked at some finite size differences because chameleon theories, they sort of shield the local gravity. And here you can see that this dark blue is for when we take the shielding into account, and this is where we say that the model the system just as a point mass. And in this case, you can tell that the extended system is actually not very. You have this. It gets worse. And if we now compare to these existing bounds in pink, we were able to do a little bit better in this case. And this might look much better than this, but the transformation between these areas is very non-trivial. These plots contain the same information. And here we have essentially assumed that you can reach very good vacuums in the experiment. And we think that's why it did really well. I think I am, so just to talk a little bit about ongoing projects that we have now. So together with Niklas, we're looking at can we now use these optomechanical systems to really prepare these non-classical CAT states, which could then be used for sensing. And we're doing this together with Sumio Bratta as well. Another project we have in the group is to look at can we use quantum sensing to turn inwards instead, so not look at external effects, but look at quantum technologies and see can we use it for benchmarking and calibration of devices. I also wanted to highlight here this initiative called DRD5. This is a CERN initiative, and it's concerned with how can we use quantum sensing to improve particle physics detection. So here I am one of the work package leaders on sort of trying to scale up quantum effects. And this is a quite loose initiative, but any ideas or membership, you can become a member, I think, if you have a university affiliation. If you're interested, let me know and I'll put you in touch. So there are various workshops happening as part of this. Okay, so that is everything for me, and I think I hopefully finished on time. So if you're interested or if you have questions, I'm very happy to chat, and I sit in the office over there. So just come by at any time or drop me an email. Okay, thank you.
Sofia, now we have time for any questions.
So, sorry. I'm interested in, well, vacuum, quantum field theory, and all these things, right? So when you mentioned this idea of having these time-dependent, let's say, additions on top of a background interaction that is there, right? There are many particle effects in quantum field theory that depend on external forces for finite times and all this. I'm sure that you have at the very least one work that is related to that. But overall, it's can quantum sensing help us in this direction too, of kind of probing, I would say, without photons? Let's put it this way. Is it possible to try to use this idea to probe a cavity with no photons in it?
I don't see why not, in the sense that, it would come down to how you model your interaction, in the sense that the optomechanical Hamiltonian explicitly needs there to be photons coupling photon pressure-wise to the mechanical elements. But if you had a levitated system and you consider like vacuum fluctuations and how they push and pull the oscillator, then I imagine that would lead to extra noise. And one thing that's very nice with these systems is that, at least for levitated systems, the noise budgets are extremely well known, which is why they're used for these collapse mechanism detection cases. And in that case, you have to, the key idea is that the noise is really low in these systems, and then any additional noise you might detect could be due to these localization events as part of the collapse theory. So if you wanted to look for vacuum fluctuations, I think there might be better ways suddenly to maybe to do that. But if you could model that as affecting your mechanical system, which is quite large, I guess, compared to also single atoms, that would be quite interesting. I also know there have been some recent works on cooling with like dark cavities. I can have a look and we can chat more. So when you specifically don't want, so optics is very noisy, so in these cases you don't want optics because it also introduces noise. So there have been some nice ideas on how you do things without a noisy optical state. Thanks.
Right, so with that, thanks, Sofia.
Thank you.
Next up, we have
that one.
Sergi Nadal-Gisbert.
Yes, and I will give you this as well.
Okay. I may need something to adapt.
So if you look there, you can pick your...
Okay, I see.
Okay.
So you can just align this thing.
Here? Does this work? No, I should connect it. Never mind. Okay. Okay, so first of all, thank you for giving me the opportunity to come here and speak about my work. And I would like to present you some ideas related to entanglement in quantum field theory that I've been doing in collaboration with these people. So I will be discussing how to construct partner modes in quantum field theory and how these ones can tell us information about entanglement between local modes in quantum field theory. So, as Rick already mentioned earlier, the vacuum of a quantum field theory contains quantum correlations between different regions of space. And this brings us to the question of what happens if we have a single mode localized in a given region. How is the entanglement of this mode distributed in space? So in order to answer this question, we will construct the partner mode of this mode A, which is another mode that contains all correlations with A. And I want to emphasize the use of complex structures and the complexified phase space to construct these partner modes. Okay? So this has potential applications in Carter spacetime, especially, for example, in black hole formation and evaporation, trying to understand where the partner that is correlated, fully correlated with the Hawking mode lives in this spacetime. So let me introduce the techniques that we will use to construct these partner modes. So we are dealing with quantum field theory and Gaussian quantum mechanics. So in this canonical picture, we will have operator value distributions, which are the field and the conjugate momenta, satisfying some commutation relations given by the symplectic or the inverse of the symplectic structure, which will give us some symplectic product. And then, because we have also quantum field theory, we have phase space elements that are functions in space. Typically, we choose them to be compactly supportive functions in Carter spacetime. And there is a one-to-one correspondence between functions in phase space or phase space elements and linear observables. So using the symplectic structure, we can build linear observables in the following way, where we have some function smeared with the field operator and some other function smeared with the conjugate moment operator. So regarding the state, we will be focusing on Gaussian states because these encode all the information with the first and second moments, and therefore we can all the information is contained in this covariance metric where we are using centered operators to remove the first moments. And this contains all the information about the state. However, we want to shift the attention from this covariance metric to the complex structure, which is linear in phase space. So this is another object that we build from the covariance metric and the symplectic structure. And the main advantage is that because it is linear in phase space, we can ask whether it has eigenvalues. And it turns out that it has eigenvalues that come in pairs, and these are typically called the symplectic eigenvalues in quantum optics literature. So this object will be the key object to construct the partner modes, and this is because of the following. So we will consider a subsystem, which is a subspace, a symplectic subspace of the complex phase space, and this subsystem or a given subsystem will be uncorrelated if it is left invariant by the action of the complex structure. So whenever we have this quantity satisfied for a given subsystem, the action of a complex structure leaves it invariant. It means that the state is separable in the following way. So we have A and the complementary degrees of freedom, and we say that subsystem A is uncorrelated. So using this definition of an uncorrelated subsystem, then it is straightforward to construct the partner mode, and this will be the mode such that together with mode A give us an uncorrelated subsystem. So the subsystem A and the partner will be uncorrelated. So the action of J into the joint subsystem of A and its partner will be the same subsystem. So this gives us the following very nice expression, which is just the action of J into subsystem A and the projection onto the orthogonal complement of A. And this is the partner mode subsystem that contains all the correlations with A. Okay, so yeah, this subsystem or this partner construction agrees with previous results obtained in other contexts. But the main advantages are that this is a concise and mathematically transparent expression. It is basis independent because we are defining subsystems in a basis independent manner. And more importantly, it is useful to extend the notion of partners to mixed states. And this is something that I will not have time to talk today, but that you can check in this preprint. Okay. So good. So we have built this notion of partner mode. And in quantum field theory, I was mentioning this idea that we have some mode localized in a region. And now applying this formula, we can construct the partner mode of this mode A and check what are the properties of these modes. So we can see that the partner mode will be spread all over space, and it will be controlled by this complex structure function. And because of that, in Minkowski spacetime, we'll have a decaying behavior of 1 over the distance square and 1 over the distance to the 4th power, equally as field-field correlations and momentum-momentum correlations decay in Minkowski spacetime. And the typical interpretation that one does is that this partner mode profile is telling us where correlations of A are located in space. So now, keeping this intuition in mind, we can ask the following question. So in which precise sense the spatial distribution of these partner modes can tell us information about the entanglement between two modes A and B? So for example, here we have one mode A, one mode B localized in different regions, as Rick was mentioning before, for example, and we want to understand if the partner mode construction can tell us something about how these two modes are entangled. Okay? So for this, what we do is we keep using these techniques of complex phase space, and we build the following overlap notion between a given mode, between B, for example, and the partner of A. So this is telling us how much of B is contained in the partner of A subsystem. And we realize that this overlap notion can signal the presence of correlations between A and B. Okay? This is something that we check. And in order to build a correlation measure, we use the symmetrized construction under the exchange of A and B. And now we can relate this symmetrized measure to a necessary and sufficient condition of entanglement between A and B. And what we find is that this necessary and sufficient condition for A and B to be entangled is the following one. So we have that the overlap measure has to be bigger than some threshold, which indeed depends on the purities of the reduced system AB and the joint system AB. And this threshold measure increases also with the mixedness of the AB system. Therefore, now we have an interpretation for the entanglement between A and B, which is the following one. So there is a competition between the overlap with the purification partner modes and the mixedness of the reduced state as determined by this threshold measure. So this competition is telling us whether A and B, these local modes, are entangled. So I will summarize these main ideas that I have shown you. So we have seen that complex structures are central to study correlations in quantum field theory, especially in Gaussian states, and that this complex structure J tell us how correlations are distributed in space. Finally, we have used this partner mode construction to determine whether two modes are entangled and to find a relation between these two. And we have seen that there is a competition between the overlap with the purification partner of the other mode and the mixedness of the reduced state. And with this, I will finish here. Thank you for your attention. So, some question.
So thank you. So if you have any questions.
So this whole idea of looking at local modes in quantum field theory, I mean, I find it super interesting. The work you guys are doing is amazing. My question is about this competition between the overlap and the mixedness. Mm-hmm. So it's so let me share some results that I have but are not published yet about okay. Most entangled modes in Minkowski and 3+1, so between two spheres, right? Mm-hmm. So what happens in that case is that, well, the entanglement decays very quickly between the two. But like with the distance,
okay.
with the distance, but what's also interesting is that the impurity of these most entangled modes also decreases exponentially.
Yeah.
It decreases a little bit slower, but it also decreases right exponentially. So it's just a. So what you're saying is that basically there's this overlap between this with the partner modes. And this overlap also decays, well, you said here polynomially, or...
I didn't say how it decays.
Okay, sorry, so what decays polynomially then? Because this will be the overlap, but the partner mode, you just said that it's the correlations, the J itself will decay polynomially, right?
Yes. So
I'm trying to understand...
behavior is given by the two-point function actually, right, of the field.
Yeah, but but in this case, now you have this correlation which is polynomial, and then you have the exponential decay of impurity. So why doesn't the entanglement also decay polynomially? Because now you have the impurity decreasing exponentially.
So let me see if I get it. So you have these two modes, right? And as you separate them, you have like this purity or impurity decays exponentially, as it does also the entanglement. Yeah. Yes. Okay.
Yeah.
So I'm saying that so here this polynomial behavior, it's only between the entanglement. So this is for A and the partner, right? So there is this fall off behavior, but the entanglement between two modes doesn't have to fall in that way.
No, but now you're computing the overlap, right? Between the
Now I compute
partner,
the overlap,
which is
between A, and the partner of B, right?
Yeah.
And
but then the partner of B or the partner of A in this case, that should decay polynomially. Like the correlations between this and A. Let's put it this way, right?
Yeah.
And now you're computing the...
Yeah, that's proportional to the correlations between A and B, this quantity. I didn't show it, but...
Okay, but I'm just trying to understand how... Because my intuition tells me that the entanglement decreases exponentially with the distance. And so far, you haven't mentioned exponential, you've only mentioned polynomials. So how can I look at this D and see an exponential decay coming out of that? Is there a good way? Let's put it this way. Do you have a good answer, a short answer for this?
So, I mean, I don't have a short answer for that. You have to compare these two things and see how these two things compare, like the difference decay actually, right?
So you're saying that in your case, the mixedness would also decay polynomially in such a way that the difference would be exponential?
Exactly.
That's what you're saying, okay.
That's what I think, but...
Okay, we have to talk more later, yeah.
I mean, this condition is something that comes from the PPT criteria between two modes, right? So, but yeah, I would need to think it more carefully.
No, yeah, for sure. Let's discuss more later. Thank you.
Thank you.
All right, so thank you very much. Next up we have Santeri Salomaa.
Let me see if I
How do I connect to this one?
There should be a little this way thing. Yes.
Just plug it in.
Yeah. Yes, it should be a port that way.
Hello everyone. We'll check first that. Okay, it works. My name is Santeri Salomaa and I'm a PhD student in the University of Helsinki. And in this talk I'm gonna present paper we put in archive like a month ago with my supervisors, Esko and Sergi. And Sergi you know from the previous talk. And the title of the paper is the same as this talk, Bipartite Entanglement Harvesting with Multiple Detectors, as illustrated there. Okay. So I first give an introduction and then I go to the main two parts of the paper. So first about motivation and some general big results on QFT vacuum entanglement, which you also, some of these you have heard today before. And a fun place to start is from Rees leader theorem, which is very non-trivial sounding and interesting, which explain the entanglement of the vacuum. And so given any arbitrarily small region in the space-time, you can generate with the local operations, you can approximate any global state arbitrarily well. It sounds a bit problematic. And the famous example is if you have this OEC like your laboratory, and if you could access all the local operations by suitably operating in your laboratory, you could create Taj Mahal in Moon. So this is a famous and provocative example by Reinhard Werner. And of course, and unfortunately, you cannot access the full local algebra. So you cannot use this like a superluminal signally sounding. But the point here is that the vacuum is non-separable across space-like separated regions. Then another one that also Rick at least mentioned in his talk is the area law. So given some time slice and some region in the time slice A, let's say, the entanglement entropy scales with the area of the boundary, which this illustration is only this line. And if you think, and the problem kind of is that you need the UV regulator there, because this is in the continuum is UV divergent quantity. And the RQI way to do it is to use detector models and entanglement harvesting, which I will explain. So we focus on the last part only. Just wanted to motivate some results, big results. Okay, let's go to entanglement harvesting. So, and with multiple detectors straight away. And let's start by having some Unruhde-Witt detectors here coupled to the scalar field in the background. With this, so they start all with the ground state and they are separable state initially. And then we introduce the interaction Hamiltonian, which is the same as Rick's group and Marcos and Sebastian, I think had a time independent, but elsewhere, anyways, it's a bit similar, but now we have the sum there, so we have multiple detectors and some finite amount n. And you can have some smearing with the field if you like, or having a point like detectors. And the chi there is the switching function. Nu is the detector's monopole moment, generating the excitations. And yeah, then it's the smeared field. Okay, so this is the setup. Then we do perturbative analysis with this interaction Hamiltonian. And so the time evolution you get from the Dyson series with this interaction Hamiltonian. You get this series with the coupling constant. And I have put the first two corrections there with the, when you expand the U as a series. And then we only focus on the detectors, so we trace out the field. And interestingly, all odd correlations or corrections go to 0 when we trace out. This is a property of the vacuum. So in the end, the leading order comes with the second order. Okay, we have the setup, and then we want to see if the detectors got entangled. So I here tell you about our quantifier, which is the negativity. So it is defined like this. So you have the detectors reduced density matrix. You do a partial transpose with some bipartition with some detectors. And then you calculate basically the negative eigenvalues. So very straightforward and easy. And it's an entanglement monotone for mixed states. So for all separable states, we get that negativity is 0. And importantly, under local operations and classical communication, we don't increase the negativity. And this has a bit of a caveat since we have multiple detectors and negativity is no longer a faithful quantifier, so we can get undetected PPT entanglement in principle. But when we have positive negativity, we know it's entangled for sure. And then you might think like other nice properties for the quantifier, for example, additivity might be nice. So you might think that, oh, now I introduce logarithmic negativity, which is additive, but no. Because if you look only at the perturbative correction in the leading order for the negativity, that is additive, actually. So what I mean is I have multiple independent bipartite systems, and I look this in the total. I get the negativity between A and B sides additively as like a sum there. So it's like a, so actually negativity is very nice when you look only at the leading order because it's additive, the first order correction. Okay, let's go to the first part of the project. So where is this leading order negativity encoded in the detector's density matrix? Well, I give you an example with the two detectors first. And some people familiar with two detector harvesting may look this looks a bit off because I have ordered the bases in a different way than usual. First I put all the one excitation sector and then the rest. And it forms this block matrix, a block diagonal matrix. And then next we need to do partial transpose. What happens? Well, the two, like the x, some x's and c's get swapped. And what are the symbols? For completeness, I'll plug it in here. Some people use the c's and p's as like a cursive L, might be familiar, and the x with the cursive M. But yeah. And the indexes is like I and j is like between ith and jth detector. So okay, this happens. Very interesting because the block diagonal structure remains. And then we need to calculate the eigenvalues, right? Well, for block diagonal matrix, it's very easy because we can look both blocks independently, and we find that only the first block contributes to the leading order negativity. Because when we calculate the second block eigenvalues, we get the two high order terms for the leading order negativity. So very interesting, only this block seems to matter, right, if we only consider leading order negativity. So what happens in general? Is this just for dual detectors? Well, no. This actually happens in general with any finite amount of detectors. So when we do the block, initially we have the block diagonal structure, and then we do the partial transpose, it remains the structure, and the first block is the one excitation sector, and it gets transformed in a very simple way that where we have two different subsystem indices, then the X's and C's get swapped. And only this one excitation sector block contributes at leading order. So why is this significant? Is that if we have multiple and multiple detectors, a reduced density matrix for the detectors like explodes exponentially big. But if we only consider and care about the leading order negativity, we can only focus on this tilde rho 1 block, which grows linearly. So this is very doable. Okay, that's a nice result. Now let's use it for something. So the setup for, so what do we do? We vary, we fix some amount of detectors first with both subsystems, and then we vary the spatial arrangements and see how the leading order negativity changes. So it's kind of like an optimization if you want to maximize it. And the constraint is that we keep the subsystem detectors causally disconnected, so there is some minimal distance between the different subsystem detectors. And this is because we want to only consider the genuine entanglement harvested and not the causal signaling. So this big L is the smallest allowed distance between different subsystem detectors. Okay, let's do it. And let's start with 3 detectors because 2 is boring, trivial. So let's vary the position of number 2 detector here. And let's keep it out of this circle because then it's too close to the different subsystem detector. And let's see how the negativity varies. And then this is the block which we're interested because that contributes to the leading order only. Okay, let's do it. And this is the one picture of the, or plot from the analysis. And it seems that when we place the detector 2 on this opposite side, we get most entanglement, or at least most leading order negativity. Okay, so this is the optimal arrangement with 3 detectors. And later I can analyze a bit why it makes kind of sense. Okay, for detectors, there's too many new variables if we want to consider all the spatial arrangements. So in the project we considered these different arrangements with 2 and 2 bipartition. So both subsystems have 2 detectors, and then we vary the X in each of these. So we get plenty of these symmetrical arrangements we considered, but also we did asymmetric bipartition just for fun. Okay, I don't show any results, but you can check it from the paper if you're interested. But you still might be interested what was the maximal one. I will show it soon. But what are the general results we learned from this analysis? Well, is that when using more detectors, sorry. Okay, 1 minute. Okay, I'll be quick. Okay, well then I can skip these, but you can read them. Well, this is the optimal one, so we want to keep the same subsystem far away from each other, because then they don't get entangled with each other, which makes sense with the monogamy of entanglement. We want to, okay, I'll skip this one also. So these are kind of like algorithm way of looking at the results. And final one I display here is the linear chain we did with the alternative subsystem detectors. And we found actually that with any energy gap, we get a linear increase with the leading order negativity, which was very interesting. And this is now possible because of the framework. And conclusion slide, this might be interesting too. Well, yeah, this was one of the main results, that it's doable with 50 or 100 detectors. And we get larger regimes of non-zero harvesting. So we can harvest with the wider parameter regime. And who is this maybe interesting to? Maybe some experimental people who want to realize this like entanglement harvesting, for example, superconducting qubits, or then Rick was talking about Bose-Einstein condensate, or with some drop ion simulations. But yeah, and this is me working on the harvesting business. Okay, thank you. Any questions, or is there even time? Okay, yeah, sorry, I was got too excited.
So why was it switching? Did you do it what was the switching you used?
Well, we actually analyzed with a few different ones. We did the Gaussian, then we did truncated Gaussian where we cut the tails. And
but all of them just one.
Sorry?
All of them just one. You didn't play with oscillating or anything?
No, we didn't play.
That's so boring.
But yeah, we did Gaussian truncated, and then we did some compactified polynomial stuff.
Yes, thanks.
Great, shows that.
Yeah, so you're ready to go. We've got Ties-Albrecht Ohst. Yeah, go ahead.
Yes, sure. Yeah, thanks. First, thanks a lot for the nice organization. I learned a lot today already. And today I want to talk about a current work in progress, which we did here in Nordita, together with Sebastian Schuster and Rope Uala, which are also working here. And the topic of today's talk is measurement disturbance. It's not so much on the relativistic side, more on the quantum information side, but hopefully you can enjoy it anyway. Okay, to start with, I want to recall this weird phenomenon of quantum theory, which is measurement disturbance, the topic. And it's this universal feature of quantum theory that any type of information extraction that you can perform on a given quantum sample, quantum particle, automatically leads to some sort of disturbance on this particle, on the sample. And at first sight, this might be seen as a problem because, in some sense, if you destroy information by measuring, it sounds like a bit of a waste of samples compared to the classical case. But actually, it turns out that, or has been found out in the last 30, 40 years, that this is actually a very, very interesting and important aspect of quantum theory when you consider quantum technologies.
One example for this is the BB84 protocol used in quantum key distribution or in quantum communication. And here, like the very simplified version of the idea is that one encoder or one sender wants to encode a bit of information in a qubit or a two-level system. And the encoder or the sender does this by either performing like the encoding in the Z basis or on the X basis. And whenever some eavesdropper wants to get a hand on this information, they have to opt for either measuring in the Z or X direction, but without knowing which the actual encoding basis is. And by this, in 50% of the cases, the eavesdropper will be successful and will encode the right bit. But also in 50% of the cases, the eavesdropper will measure in the wrong basis and disturb the state into the maximally mixed state on average. And on the one hand, he doesn't learn the information, and even worse, he disturbs the system, and sender and receiver will quickly understand that they don't have like a secure connection. This motivates like the guiding question of this project, as measurement disturbance is interesting. What is the fundamental limit on measurement disturbance with respect to the observable information which can be extracted from the measurement, and how can this fundamental limit, if it exists, be measured in practice? There are two important quantifiers or parameters of measurements that I use here. And as measurements, I use generalized measurements, so positive operator valued measures, short POVMs. And the first one is the so-called informativeness. The informativeness answers the question how reliably a measurement can decode information of a quantum system. And in technical terms, this can be seen as the maximum probability with which I can trigger a certain measurement outcome by preparing some state. And in mathematical terms, it's defined, the informativeness of a measurement or a POVM is described by the sum of maximal eigenvalues and of the measurement effects, and then with the normalization factor 1 over the dimension in order that this quantity is bounded by 1. The second important parameter here is the disturbance. And the disturbance is usually, or we go by defining the disturbance in terms of the so-called average fidelity. And the idea is that you can assign to every quantum channel the average fidelity, which is just the average over all input-output state fidelities. And since there might be some choice or some prior knowledge about your input states, you also have this possibility of changing the underlying state ensemble, which is given, or which is mathematically given by some measure on your set of input states. Okay. It turns out some people in the past already thought about the connection between information and disturbance. And in particular, a very interesting and important result is by Konrad Banaszek in 2001. And there he proved that if you have a POVM with m outcomes in a d-dimensional system, and then if you then look at the channel which is given by the square root measurement, or people also call this Lüders instrument of this measurement, and if you also consider as your input ensemble just H random states, then it turns out that the average fidelity of this square root channel is upper bounded by some function BD applied on the informativeness. And moreover, this function goes from 1 over d, lives on the interval 1 over d and 1. And it turns out to be monotonically decreasing. So one can explicitly write down this function. It's a bit lengthy, but here you can see the function plotted for dimension 2 to 4. And one can argue that this is actually a really interesting and useful technique to bound measurement disturbance in a very simple manner. Because one can argue that getting lower bounds to the informative is relatively easy. Just prepare some states and then record the probabilities with that you measure your outcomes. And if you sum up these probabilities, you get automatically a lower bound to the informativeness. And since this function BD is monotonically decreasing, you will get in final an upper bound for the disturbance of your measurement channel, which is quite useful. And also interesting is that this only uses pure statistical data, so we have no idea about the post-measurement state. And we only look at statistical data because as input we just have our measurement. And they suffice to quantify a lot about the disturbance of the measurement. And the question we asked ourselves is whether one can generalize or improve this. And so our goal, or our research goal here, is to find like a universal quantifier that allows to use all the statistical data about your measurement. So you look at state variations and probabilities. With that, you can bound the measurement disturbance that is possible, or like the least measurement disturbance which is possible to be achieved by the given measurement. And we thought about this, and we came up with the following construction. So we define as the so-called statistical disturbance bound the following maximum. We take the maximum of average fidelities of quantum channels, and these quantum channels have to be compatible with the underlying measurement which they have to model. There's some freedom because it turns out that any quantum measurement has many possible measurement channels. And if we now optimize the average fidelity over all these measurement channels, this is what we call the statistical disturbance bound, and it gives rise to the minimal amount of disturbance that is possibly achievable by a given measurement. And what is also very, very good is that this quantifier is actually efficiently computable. When you give me the measurement operators, there's this technique called semi-definite programming, which we use a lot, and you can actually compute this statistical disturbance bound, this maximization, by a semi-definite program. Okay, we came up with this quantifier, but is it good for anything? That's maybe the first question one should ask. And there's actually a very, very simple example which already sheds some light why this might make sense. And we compared two different error models of a very simple two-dimensional measurement. So we just look at the standard sigma z measurement, and we look at two error models there. The first error model is noise, or white noise, and this describes the kind of error that you get a random outcome with a certain probability. So let's say with probability p, for any given input state, we get a random outcome with probability p. So for example, if we prepare our state in 0, perform the measurement, in 90% of the cases we get 0 and 10% 1, because even in 20% of the cases we also are right in 50% of the cases. This makes sense. And it's very easy to compute the informativeness of this measurement. It turns out it's just given by 2 minus p half. And a different error model is given by losses. So here we always got some measurement outcome, but maybe sometimes your detector doesn't click, or if you have a photonic experiment, your photon might be lost to the environment before your detector even captures it. And if you want to properly model this, you actually have to also take into account the so-called no-click event, where you neither measure 0 or 1. And this is called like the nothing or no-click event. And also quite intuitively, the amount of information which you can learn compared to this noisy and lossy measurement are exactly the same. And also, if you do the math, it turns out that the informativeness is again given by 2 minus p over 2, as in the noisy case. But if we now look at our quantifier, the statistical disturbance bound, it turns out that in this case, or if we look at the Haar ensemble, we can actually compute this quantifier analytically, and we got completely different behavior for these two different error models. I mean, apart from the case where we have p equal to 0 or p equal to 1, we see that the behavior is very different. We get a linear scaling in the case of losses and a non-linear scaling in the case of noise. So while this Banachek bound, this information disturbance bound, cannot really tell them apart, cannot tell them these error models apart,
the statistical disturbance bound that we introduced can. Okay, that might be nice, but so far this estimation of F, or statistical disturbance bound, relies really on the mathematical description of our measurements. And this is in practice often not realistic. So often you do not have a full error model, or like you're not sure about the full valid error model of your given detector. And this opens the question whether our quantifier can also be measured without knowledge of the underlying measurement. And this turns out to be possible. And a task which we call weighted quantum state exclusion. The idea is that you can prepare any kind of states, let's say, which are possible with your experimental setup. Like, for example, if you have a two-level system, let's say you prepare sigma z, sigma x eigenstates. And then you collect the measurement statistics for all of these states. So, for example, for the 0 state, you get this kind of histogram, and for the plus state, you get this kind of histogram. And we know by Bond's rule that the probabilities, or like the bars in this histogram, are given by the trace of our measurement operator and the given state that we prepared. And now it turns out that if we sum up these probabilities, all of them, and we also input some weight terms, which we call here QAI, it turns out that this quantity here gives rise to an upper bound of our statistical disturbance bound. In case, okay, like here I cheat a bit, but here in case that some operator which linearly depends on rho and q is positive semi-definite, but this is also, again, one can easily ensure this by semi-definite programming. So the idea is that one would experimentally calculate or like estimate these probabilities by having enough samples of states, and then optimize, minimize over these three parameters while this positivity constraint is still fulfilled. Okay, but with this, I would also come to an end. I hope, okay, first in this talk, I hope I conveyed that it's also interesting to think about measurement disturbance. And in this project, we developed the so-called statistical disturbance bound. And the idea is that we want to optimally quantify the disturbance of a quantum measurement based only on the statistics without any information about the actual post-measurement state. And I also showed you that this quantifier can be measured also efficiently using this framework of weighted state exclusion. And as an outlook, we would like to use this quantifier to design measurements of a very small disturbance, or possibly small disturbance. These questions play a role, for example, in the study of joint measurability, where one has like measurements from which one coarse-grains other different measurements, and it might make sense to apply this technique in this setting. And also because this is a workshop on relativistic quantum information, I think it's actually an interesting question to ask how space-time geometry comes in here, because I suspect that when we look at, for example, detectors in space-like separated regions, I suspect that the disturbance bound for them should be actually even higher than in the, or lower, like the fidelity should be lower than in the non-relativistic setting which I discussed here. But with this, I want to thank you for your attention.
Thank you very much. Probably have time for one brief question before the coffee break.
I hope it will be brief. Thanks for the mic. Thanks for a very interesting talk. So I'll be maybe more technical with the question to be briefer. So if you dilate your measurement to some unitary interaction, that seems to be very similar in spirit to looking at decoherence from interaction with some environment. So, I mean,
yes.
Does it lead anywhere are there any techniques that one can import from one or the other study to either use this semi-definite programming maybe to understand the coherence in context where maybe it's harder, or vice versa? Does this connection make any
I think
difference here?
what we did is I think we essentially found a different perspective on exactly that question, because as you said, every generalized measurement can be understood as a projective measurement with some auxiliary space. But of course, this also includes like the noise description. For example, the depolarization noise which we had here, or we also looked at different kind of noise models. And with this, we can study these kind of noise models with respect to their disturbance, or like the disturbance of the measurement on which these noise models act. So I think this is like studying like these unitaries in the dilation is like an equivalent task, I would say. And it's like just our perspective of just staying at this POVM level and working out everything there. But I think this is like an equivalent formulation which you mentioned.
Okay, thanks. I'll ask some more details later in the break.
Right, so for the first talk of this session, we have Magdalena Zych, who will be talking about exploring the interface of quantum theory, relativity, and gravity with atoms and light. Take it away when you're ready.
Thank you very much, Cinzia, and thanks everyone for showing up after 2 busy weeks of the events that you can see here on the posters. I didn't put credit. The posters are done by Sebastian Schuster, who will be speaking, I think, right after. So watch the next talk on YouTube, wherever you are accessing this repository. Without further ado, we'll just put a bit of placeholder to start and introduce our group here at Stockholm University. So my position is funded through the Wallenberg Academy Fellowship, and I currently have the privilege to work with Evan, Germain, Jerzy, and Sarah as PhD students, and Sebastian and Navdeep as postdocs. And we are interested in various topics across quantum and gravity foundations. I would like to highlight some topics which perhaps can be useful if you are wondering whether there can be something interesting to work on when you come here. So I'm to highlight some directions that are maybe not all as active now, but in general I have interest in them. So this will be in general the spirit of this talk, to kind of highlight various directions one can take, and also just very, very on a high level, the research that is done here, without going into any details, because there will be all the talks after me that will do that much better. So I have interest primarily in answering the question, what are unique phenomena, the interface of quantum theory and relativity, and in particular relativistic gravity, and how therefore we can test the regime where both of these theories are required to describe the phenomena. Also the topic of indefinite causal order, and especially where gravity might come in. I still have some interest in some tests of alternative models that are often inspired by the coherence or come from some ideas about constraining the ability of, for example, gravity in transferring information, and very, very, very generally, any foundational questions about quantum field theory and space-time, quantum or classical. So why? I think an honest answer is why not, but I felt I cannot quite put it. So this is a diplomatic version of why not. Yes, because we want to test foundational theories that we have. We want to understand to which extent they are capturing how nature is. We might want to test some very basic principles, to which extent they apply, even if we don't have access or we don't know what the next theory should be. And it's also interesting to explore the mathematical structure of the theory, to kind of push it to its extreme and try to understand what the theory entails, and that more broadly in science can be useful for building interpretation of theories and engaging with questions like what's the right ontology for the theory, for example. And also, I think it's important to understand not just the limitations, but also applicability of our frameworks. Because I believe that sometimes we think that the frameworks we have are more restricted, but in fact we can capture scenarios that we would think maybe already pertain to quantum gravity theory. And if there is a chance, I'll say exactly one sentence about how that can be achieved. And of course that's relevant in terms of connections between quantum and gravity, and what are the scenarios where we need or don't need quantum gravity actually turns out to be somehow a matter for discussion, while one would think that it should be crystal clear. So I found it particularly interesting as well. Why now? And that's of course because we have better abilities to test. And I guess I'll not delve more on this. And so the plan for the rest of the talk is to mostly focus from the structural perspective, and that might be interesting to see that there is some core of the methodology that we have that can be seen playing various roles, and then also maybe can explain how various extensions or generalizations came about and what their physical interpretation might be. Yeah, so my research largely originated from thinking of composite particles as clocks, and if you've and many of you have attended the school 2 weeks ago and the conference, so that is probably very familiar. So here the notion of a clock maybe should be read as quote unquote, because not everybody would call it a clock, but the meaning of that word in this context is essentially any system that is sufficiently small that can be considered approximately point-like, but has some internal degrees of freedom. And so in typical conditions, an atom would be a good candidate with electronic internal levels in the center of mass. When internal energy of relativistic systems is quantized, this can be seen as a system with quantized mass energy. So such systems can be considered not just as quantum clocks, but also quantum test masses. These systems can be coupled to external fields, and a system with an internal qubit coupled to a field is very well known, very under various names, being an Unruh-David detector or a Jaynes-Cumming model. So such a system can also be considered as say extension to those models where you treat a quantized center of mass of those quantized two-level systems and include that in the dynamics, not just the interaction with the field. And also it can be, such a system can be thought of as a thermometer, because if you have internal states, again, interacting with some external environment, once you pick the right interaction, you can study thermalization. And so you can have a model of relativistic thermometers, and that can be interesting as well, especially if you've heard about Unruh effect, that says when you have an accelerated system, it will thermalize. So if you have an accelerated thermometer in a vacuum for an inertial thermometer, the accelerating one will thermalize, and you can study various quantum aspects of that, for example, when the motion is not classical. And with this, maybe I'll highlight some structural reasons one can also be interested in these systems. And later on, I will tell a bit more about particular approaches or questions within each of these categories. So I think it's underappreciated that these composite relativistic systems at low energies, they actually have their own symmetry. I mean, at arbitrary energies, they have their own symmetry, because if you've heard about classification of particles, that they are given by mass and spin. If you have something with internal mass energy, then it's essentially not an irreducible representation. So it's essentially a central extension of the Poincare group, but it doesn't have much consequences when you think of the Poincare group. But when you go to low energies, where you still have relativistic effects, the symmetry is central extension of the Galilei group. And this is a particularly nice regime that can be interpreted as center of mass being effectively non-relativistic, but your internal dynamics being fast enough that can pick up time dilation effects from this low energy center of mass, and no other relativistic effects. So it's essentially the regime where the only relativistic effects are the lowest order time dilations or redshifts. It's very relevant. It's essentially at the heart of the debate about the mass superselection rule, and also to understand semi-classical motion of such systems can be done by looking at different uncertainty principle than the usual phase space one. And again, I might mention a little bit about this later when we look at the kind of questions that can be studied within each of these streams. So this is just a set of three hooks, hopefully, for people that are theoretically minded. Why this regime is interesting not just maybe from practical perspective of modeling specific effects, but it can also be very interesting from just very broad theoretical mathematical physics perspective. So in terms of this system as quantum clocks, I've just given a low energy Hamiltonian where I capture this internal energy as mass, and one can study such systems in interferometers. So I just highlight recent work from our group with Jerzy and in collaboration with Josh Fu, looking at the specific trapped interferometer where such systems can be studied, and one can ask what's our chance to see this quantized coupling between internal energy and the position. One can study such systems trapped, and they are then quite close to how one models optical atomic clocks. And such simple model can also reveal either underlying explanation for effects that are considered semi-classically and new effects that can also be looked for in experiments from the point of view of testing such relativistic corrections in quantum composite systems. From the perspective of such systems as quantized test masses, one can simply look at how they propagate and ask about the validity of the equivalence principle for such composite systems. So very broadly, equivalence principle in this regime will call for inertial gravitational rest mass. So these three different masses, in principle, I can consider could be different operators. And classically, that has been how the equivalence principle is studied, and one assumes that, say, inertial and gravitational mass could be different. This regime, the most general difference you can have is that these are different operators. So it's an interesting point of view on what does it mean to test equivalence principle, and it also settles question whether or not it's fully equivalent to classical physics or not. And here you see that it's different even from the point of view of how many parameters you have in order to essentially state that three operators have the same eigenvalues in spectra. In classical physics, this problem was reduced to just spectra. So you already see how even being very agnostic about where this is coming from, it already tells you that in principle there are more questions that you need to ask and answer to verify this. And just looking at the propagation of such systems, one can ask what are states of such composite particles that would move the whole particle together with all the internal states and realize a semi-classical trajectory, like as we would consider saying a wristwatch on an astronaut traveling with them on the same word line. And it turns out that there is a particular mathematical expression for states that satisfies this. That is not just the usual Gaussian wave packet times any choice of the internal states. Now, when you couple such systems to external field, there are many more things you can do, and they come from starting from all these different prior uses. So you can start from where traditional way these systems were used as a two-level system on a classical trajectory. And you can consider there is some extra degree of freedom, non-dynamical, but nevertheless quantum, that decides which trajectory such a system takes. So we can have, in that way, quantum-controlled superpositions of trajectories for such a system. And if you think in terms of experiments, so typical experiments with the atoms in the interferometers are such that you faithfully capture the results of the experiment if you consider that the atom takes one of the two trajectories through the interferometer, but each of these can be approximated as a classical trajectory given initial conditions given by the beam splitter. You can also consider such a degree of freedom that can control various different things about this detector when it interacts with the field to look at some indefinite temporal order of the interaction events. And you can also commute it, so to say, to control some parameters of the space-time that decides the quantization of the fields. So you can start to build some kind of phenomenology of non-classical space-time models, and then use this essentially as a tool to start to build some phenomenology, so that you have some concrete results, so as to what a particle interacting with a field in a space-time whose some of the parameters depend on some quantum variable, like what would it do? But it allows also other types of extensions that just come directly from thinking in terms of the dynamics that I shown before, because nobody stops you from considering the entire dynamics of the center of mass. And we've looked at this before with Evan and Caroline in respectively the low energy and the fully relativistic regime. So it's interesting that it's actually feasible, and it's again very interesting from the point of view of foundations, because one finds out that the way you capture the center of mass of this system, whether you come more from field theory or more from relativistic quantum mechanics, actually at some point makes a difference. So perhaps there would be at some point a way to test which is more appropriate model for particular physical realizations. And finally, these systems can interact with quantum fields in some dynamical backgrounds, like in the presence of gravitational waves. And I expect there will be more about this coming in later talks in this session, so I'll leave this topic at that. So let me then just highlight that one can, with all this, one can start to see that actually the distinction between fixed background and the systems moving on some quantum control trajectories in scenarios where some aspects of the metric that decides the fields are quantum controlled are actually not as different as one would think. And in fact, we claim that they are equivalent. So there will be scenarios that one would think represent some phenomenology of quantum gravity, but they are actually fully formally equivalent to just quantum matter or fixed background on fixed background. And so in this way, one can probe applicability of the formalism and actually find out that it's that some of the scenarios where one would think are already probing some physics beyond our standard formulas are actually not of the type. And in particular, we show in this paper that scenarios that include gravity-induced entanglement are exactly of that sort. So that perhaps will motivate some people to have a look on our paper. It's in press, but it's available to read already. So the last thing I'll mention very briefly is thinking of such systems as thermometers. And I think if there are some people that have not yet heard of Tolman effect, I'll just very briefly explain, and they will immediately see why people in RQI would be interested in thermometers beyond just Unruh effect. So there is a so-called Tolman effect that tells you essentially when you have a column of gas in equilibrium in the gravitational field, local temperatures are different. You can come to this conclusion thinking in terms of redshift. So if you think that this gas is in equilibrium because maybe photons are exchanged, then in order for these photons to be the right local rest frequency of your atoms, when you include the redshift, they have to you will have this redshift of temperatures that essentially capture the redshift of the atoms at different heights. So just very general. This is a very general result, and if you start to think of some quantum particle that travels through some gas that is not controlled by anyone, any particular lab, so it equilibrates and in curved space-time, then you come to the conclusion actually you are tasked with answering what's the temperature of a thermometer that interacts with different baths depending on its state. So if you restrict to just two paths for simplicity, you end up with this toy model of an interferometer where each arm you have a bath at different temperatures. So this is a coarse-grained picture of a quantum particle just flying through some gas in thermal equilibrium in an external gravitational field. And interestingly, there is another motivation that comes from considering some particles moving in superposition of accelerations. And again, if we recall the Unruh effect, we expect that depending on the acceleration, the system will thermalize to a different temperature. But when we studied such scenario with Josh in our first paper on understanding what the two-level system interacting with the field in superposition of trajectories does, we found that even if the system moves in superposition of trajectories with the same acceleration and therefore the same temperature, you would think, well, it's then the same bath and it shouldn't make any difference. Actually, it was making a difference. And at the beginning, we didn't have an explanation for it. But then in combining all the different insights and inputs, we realized that there are two different ways to model temperature superpositions. And one of it is considering some extended pure state where you trace out some part and you are in a subsystem. And then essentially, when your system travels in superposition of trajectories, your full Minkowski spacetime is this pure state, and your system sees a restricted region. But which region it sees depends where the trajectory is. So essentially, when you have spatial superpositions of trajectories with the same acceleration, you're accessing different spatial regions. You're partitioning your infinite space, but in a different way. And this is sufficient to explain the difference that we've seen. So again, there are both very specific questions in terms of thermalization of systems in superposition, but also broad questions in terms of how one can model such scenarios and what is the connection to different fundamental effects one is familiar with. So with this tour de force, I'll finish the overview of the direction and topics. It doesn't exhaust all the things we are interested here and things we do, but that's what I prepared. And with this, I'll just put up the photos of the group again, and I'll thank you for your attention.
All right, do we have any questions?
I didn't particularly make it as a research talk, so I don't mind if you have no questions, and we move to the talks from the group, where there will be you then might have specific questions to some of these. So yeah, thanks everyone for your attention, and I'll pass the mic to the next speaker. Maybe some shift. So you put your mic maybe as a first thing, so we don't forget about this, and I don't sit with it. Is there anyone that can help us?
Full screen, that would be great. I'm afraid I'm out of my depth with the Mac.
No, we don't want to try it. So I take something from them. We are trying to somehow make it full screen. So to present like this.
Like on Windows, it's Control L, but
It had just worked last with Magda's talk, right? Like, it
But
was
I
also
was
like
not
this
now. I
and-
was presenting from the PPT, and this
Oh.
is a PDF. So this.
well, but also the aspect ratio is all off.
The problem is aspect ratio.
Okay. We officially asked for help. You did not notice. Does anyone know? So this is just Adobe on the tablet, and yeah, there were some weird tools. Yes, and we tried view settings.
And there's no.
No, I don't know. We Okay, this reading mode, I think I just tried. Sorry, you see my mind
There's
is...
no present, okay.
No.
That's
Perhaps switching to a laptop.
yeah, if there is an available laptop, for sure. Is there any available laptops that you have your presentation on?
I'll quickly send it to you.
Or you do like Martin Boyovald, you just present from the phone.
That's maybe an option. I'll send it to yours. Okay.
Click anything.
I apologize for this.
Okay, so actually there's no here. Home. No, it doesn't put this back.
There's some extra menu here.
View.
Window.
Can I try exit? What is that?
Yeah, exactly. Like
I send it.
after a recent update, I mean not so recent, but after the last major update, actually, I think it's...
So what's the current plan? You're going to get a complete?
You have to download it. I'm just kind of slowly walking up there and slowly download it. So it looks like I'm doing something.
You could see what happens if you don't do mirror. But yeah, I'd have to probably change something else. If there's a laptop that might be the fastest. I'll try it.
My apologies.
And then I had a copy of it.
You're going to think of the funding situation that SU is very bad. You don't even have a laptop, you know?
I hope people online can hear me. And yeah, after the technical difficulties, I have to especially extend my thanks to Magdalena and Sarah, and potentially other people, because this is very much two projects that are still very much work in progress. So one is with my colleagues Finn and Chris. Jan, who's currently in Bremen, and Finn is in Australia at Macquarie. While the second one is a project that I started in Sheffield with Sam Dolan, and I'm now continuing with Magdalena and Navdeep, and potentially more people. Both of them are about the subject of Unruly detectors. So that means that my introduction can actually be surprisingly brief, given how much we have already seen on Unruly detectors. Still, there are some differences that are relevant in this particular case. And also, this gives me a good opportunity to give a fairly general overview of what analog spacetimes are and how exactly they work. And so, first, some caveats and conventions. So the first thing is, as somebody brought up in relativity, but I think nothing controversial here, I prefer the right type of convention. I will mostly skip over physical constants unless I don't. For writing convenience, I prefer to start with my spacetime indices at A. I hope I kept mostly to this. Now, the other thing, and this is important for the first project, I will be working for the first project with an electromagnetic analog that makes heavy use of the relativistic formulation of macroscopic electrodynamics, which is, in my experience, not too often taught. So the important thing is that the excitation fields D and H can similarly be collected in an antisymmetric tensor, like the Faraday tensor for E and B, with the difference that you now have a more complicated linear thing happening here, which you will see a bit more of in later slides. But importantly, in order for it to be relativistically invariant, you also get these funky little zetas. They're called magnetoelectric tensors. And they are important, A, for the relativistic invariance, but they are also quite interesting from a material perspective, and what makes even a linear theory like this a potentially interesting system for space-time analogues. Now, important in this context is that in gravity itself, you also have the subject of gravito-electromagnetism, which is both a mouthful and sadly very confusing if you then go in this direction, because here you actually are talking about electric and magnetic fields, which have very little to do with what the dynamics and relativity want you to tell. And that can be very confusing because the same kind of tensor decompositions pop up in these two fields in very similar ways, and the terminology will confuse people. The other public service announcement that I like to make is I prefer talking about analog spacetimes because that puts the emphasis on the metric and not so much on gravity. There are analog gravities around where people actually try to study the dynamics of gravity, but they are far and few in between. So the much better view, in my opinion, is to talk about analog spacetimes that also avoids potential confusion with certain referees. Lastly, I usually try to refer to the most easily jottable down way of references that is often the archive identifier. That doesn't mean that these are not published. It's just quick. Now, under the Witt detectors, we have seen quite a few. So this half of the slide is mostly for reminding everyone. You have an interaction Hamiltonian with a coupling, with a switch-on function that tells you when the interaction starts and stops, with your scalar field and a monopole. This is obviously the simplest case. It's not the case that I will be treating in what's coming up. But the important thing that is usually talked about and has been talked about in earlier talks is this detector response function. So it's tightly connected to the Weidmann function. And then analog spacetimes. So in practice, what you do is you look for a physical system with some kind of wave equation, asterisk. You geometrize dagger this wave equation, asterisk. And then you do curved space-time physics, double dagger. Now, in practice, this can look as beautiful as this. So this is a very beautiful illustration of what an analog white hole for surface waves on water would look like. Because what you can see is that the upstream of the water being pushed up by the fluke of the whale prevents surface waves from entering this region. So this is a very simple illustration of what a white hole for these types of waves would be. If you want, there are backup slides to talk about all the caveats and complications. Now, the first example that I'm studying with Finn and Christian is basically the idea that you can then use this specific type of a constitutive tensor, so a tensor linking the Faraday tensor with the excitation tensor, representing a uniaxial crystal. That is interesting for many reasons. A, it's just linear electromagnetism. A uniaxial crystal is a fairly well-studied physical system. And on top of it, it has some interesting features, but so it's a birefringent space-time, so you can actually view this in terms of Finslerian geometry as well, which is interesting for people coming from the modified theories of gravity community. It has strong connections through that also to modified dispersion relations, but it's still fairly tractable. The ingredients for the detector, however, have to become a bit more difficult, because you now, besides the detector world line x dot, you now need a dipole, and then on top of it, whoops, is it okay to press cancel?
They're not here. It's going to be.
It's going to be. And then you have the preferred world line U of the crystal itself, and in the crystal's frame you have its optic axis that determines the actual uniaxial crystal. So you have a bit more structure to this than to a monopole scalar field. And if you look at this from a fairly general point of view of linear electromagnetism, you can actually connect all of this to a covariant version of the Fresnel equation, which then will actually give you two metrics who together tell you whether or not a wave vector fulfills the wave equation or not. And one of them is just your standard Minkowski metric, which is sort of the most of it, but then you have the optic axis, which gives you a different type of metric with its own type of propagation speed. And this is very much early preliminary results. The interesting thing is that because of all these preferred axes, you actually get, even for inertial motion, detector responses, as long as they are not moving along the right axis. And then it basically just boils down to a sort of calculation that you would see in Jackson's book. You just decompose your vectors with the rightly chosen angles and hope that you have the patience to work through the calculation. Now, the other example that I'm currently working on in this context is an on-orbit detector for exciton-polariton analogues. And here, I will keep it a bit briefer on the formulas and give more the goal of it all, because one of the things about the detector response function is an old result by Takagi, Oguri, and then later also with a different perspective, Terashima. I very highly highlight the paper by Takagi. It's a very, very long read, but very, very good. The interesting thing about the detector response function is that depending on the space-time dimension you're working in, you will get a result that you do not quite expect. Because as long as you are in even space-time dimensions, as for example 3+1 dimensions, sure, massless fermions. Did I completely mess it up? I did completely mess it up. Great. This should be Fermi-Dirac, this should be Bose-Einstein, and vice versa. I apologize. So this will give you Fermi-Dirac statistics in even space-time dimensions. Massless bosons will give you Bose-Einstein statistics in even space-time dimensions. In odd space-time dimensions, however, the detector response function will exactly be proportional to a Bose-Einstein distribution for fermions, and for massless bosons, it will be proportional to a Fermi-Dirac statistics just because of how certain things cancel out. If, however, your mass is non-zero, you get a very complicated mess involving modified Bessel functions, cosines, coshs, sinh, sines, logarithms. It's fun if you like working with...
Just take 3 fingers and switch the screen. So slide, take 3 fingers, and then, no, slide this way, left or right. No, so, yeah, this way. So now you click.
Okay. I'm not a Mac person. So, the thing is that this is interesting in the context of analogues, because most analogues actually are 2+1 dimensional. And that is, you should be able, if you have an unrelated bit detector in such an analog, be able to actually measure these sort of differences. And why exciton polaritons are particularly interesting in this context is the mass parameter can be tuned from massless to finite masses. And another project, but that is even less developed because it requires a lot of numerics, is to study the Penrose effect in this. But so first, what are these exciton polaritons? So these exciton polaritons are a strongly coupled system of a non-equilibrium system of cavity phonons in a 2D microcavity that is strongly coupled through a quantum well to a surrounding semiconductor and its excitonic spectrum. Now, the result is you constantly lose cavity phonons to the environment, so this only ever is a functional analog as long as you keep pumping it. So it's driven and dissipative. And then the exciton modes and the cavity modes recombine to form two new modes, the up and the down modes. And the down modes are usually what you use for the analogs. And then you can actually derive a Klein-Gordon equation from these with the effective mass depending on what exactly you are pumping how, which is really nice to study the sort of statistics effects of Takagi. And in particular, after talking with Maxime Jacquet, you can use a second laser besides the pumping laser as an unruly bit detector. So this is even experimentally feasible, which I find quite nice. The other thing from a more fundamental point of view is that in most analogs you're only ever studying a Laplace-Beltrami equation. That means you're also usually only studying the conformal geometry of your analog, which is not quite the full metric, but it's really only the boundary of the light cone. Here, however, we also have access to time-like particle excitations. That means we also can study the interior of the light cone. We have the full metric information, which is quite strong compared to many other analogs, including many of the linear electromagnetism examples. But again, very much work in progress. And then lastly, and here the animation is a bit broken, I'm afraid. I'm really not a Mac person, and I have been told I am followed by a curse with every digital equipment. So I'm not yet at Pauli's level of becoming superstitious, but I'm close. So the other thing I would like to advertise, which is probably very interesting to people in the relativistic quantum information community, is that I'm part of the organizing committee of Matt Wiss's birthday conference this year, August, in Trieste. We got amazing speakers. It's bound to be an amazing place in August. Maybe a bit too hot for me, but I'm the sort of person who happily goes to Nordic countries, even in winter. So this will be great fun. I'm really looking forward to it. I'm hoping that I see many of you there. And with that, I thank for your attention and ask quick questions.
Right, thank you for the talk, Sebastian. And do we have your? Thank you for the talk, Sebastian. Do we have any questions?
So these are very interesting ways of implementing an under the width detector. But there are different use cases for these models, right? So, for instance, if you want to recover the light-matter interaction, well, fair enough. You just consider your scalar field and an inertial detector. You'll be very happy with that. If you want to do the under effect, you'll consider a detector uniformly accelerated interacting with a vacuum. Now, these are two examples where you don't need to have finite time couplings. Quite the opposite. You want to have long time coupling to either reach resonance or to thermalize, right? In the examples that you have, you see some different phenomena that are related to curved spacetimes, which are very interesting. But is there any way that you could decouple the detectors, or if you will, get these local information from the field with a finite time coupling, for instance? Or are all of these examples restricted to basically a linear interaction with a quantum field for, say, long times or in this asymptotic time regime?
I think the answer strongly depends on the model. I think for the electromagnetic case, it should be possible in principle to extend the analysis also to your sort of questions. The problem there is that from an experimental point of view, you're not really getting a lot out of it, because it's not that easy to move something through uniaxial crystal. So there is that complication. However, on the side of the on the side of the exciton polaritons, I'm not so sure what the answer would be, because I'm not as well aware of how the switching functions enter in the model yet, and how rigorous I will be able to do that. For example, the work that I'm doing with Christian and Finn very much depends on earlier work by Christian, Daniel Simpson, and Chris Fuster. That is a very rigorous algebraic quantization of these sort of systems. So they have a very tight control of what the switching functions actually do. So I think that will be fairly easy to generalize. The work that is done in the exciton polaritons is far less on the algebraic quantum field theory side. So the formulas look much more like this, much more standard theorists fare. So you would have to spend extra work to really make sure that you're in full control of what the switching functions are doing.
Okay, I guess we'll thank the speaker again.
May my curse not carry on.
Not deep now?
No, it's not done.
Is this your laptop, Sebastian?
No, this is Sarah's. Sorry. You did leave the curse behind. I did leave the curse behind.
So how long is it again? How long?
15. Yeah.
What?
Before putting it, before not on this.
All right, so next up we have Germain Tobar, who will be talking about quantum metasurfaces as probes of vacuum particle content. Take it away when you're ready.
Thank you very much. So yes, I'm talking about this work during my PhD on using atomic arrays as quantum mirrors to probe particle content from the vacuum. So the basic problem that we're looking at is, so if you think in relativistic quantum field theory, a known effect is that if you take, say, a vacuum state of the electromagnetic field, local spatial subregions of the electromagnetic field will not be in the vacuum state. You'll get multimode squeezing across the spatial subregions of the electromagnetic field vacuum. And an intuitive way to understand that is with this harmonic oscillator toy model. And if you consider a chain of n strongly coupled harmonic oscillators, so if you if you put the collective mode in the ground state, the individual oscillators themselves will not be in the ground state. And you can see that by if you take this Hamiltonian corresponding to the sum of the n oscillators and consider strong coupling between them, convert to the collective mode. If you evaluate the particle number operator of the individual subsystems, the collective mode itself will not be. The individual subsystems themselves will have some non-zero particle content when the global cavity vacuum state is in the vacuum state. So why are we interested in this? So harvesting entanglement from the quantum vacuum typically occurs at a rate too low to be observable. So that harmonic oscillator toy model goes over to the electromagnetic field if we consider the mode operator of the spatial subregions related by this Bogoliubov transformation. If you evaluate the particle number operator of the spatial subsystems using this Bogoliubov transformation, you look at the vacuum state of the global cavity. This in the vacuum, you get this non-zero particle number. So it's similar to the dynamical Casimir effect, but not exactly the same. In that here we're probing that dynamical Casimir effect in a form typically a form closer to how it was originally proposed. In that where you really change the boundary condition on a really non-perturbative length scale. And so I'll get more into the details of how that is different from the dynamical Casimir effect as it was originally presented. So the original dynamical Casimir effect involved this problem where you put a quantum field in the middle of a photonic cavity, and if you move the end of the mirror on a length scale comparable to the size of the photonic cavity, on a length scale comparable to the size of the photonic cavity, then on a length scale comparable to the size of the photonic cavity, then that will deform the mode structures. And if you do that at a sufficiently high speed, you will get a mismatch between the vacuum state of the global cavity and the new vacuum state corresponding to the new boundary condition, and that will produce cause particle creation due to the same Bogoliubov transformation I was showing on the earlier slide. So it was claimed to be observed by this experiment by Wilson et al., where you perturbatively modify the end mirror of a photonic cavity, or an analog of that where you do some perturbative boundary condition change. In this case, that Bogoliubov expansion I was showing before can be truncated at lowest order, and you get the probability to populate to the first excited state of the photonic cavity becomes this sinc function, which corresponds to parametric squeezing. So what this really corresponds to is in this regime where you only perturbatively modify the end of the photonic cavity, perturbatively modify the boundary conditions of the photonic cavity, you get parametric coupling between time-independent cavity modes. And that's important because it means the dynamics of how the dynamical Casimir effect was actually witnessed pretty much just corresponds to the same physics, parametric squeezing, that underlies many standard quantum optics experiments. So parametric downconversion, two-mode squeezing. Blue detuned pump in an optomechanical setup, also two-mode squeezing. So what we really wanted to do in this project is to move beyond perturbative boundary condition changes. So where the end of the photonic cavity is modified on or where the boundary condition changes on a really non-perturbative length scale comparable to the size of the photonic cavity. So this has been proposed with atom arrays before, where you've got this membrane in the middle with atoms laced throughout the membrane. But this also corresponded to a parametric effect. You can see that the dynamical Casimir effect in this regime reduces to this two-mode squeezing between the collective mode of the atoms in this membrane and the photonic operator of the the mode operator of the photonic cavity. So in our work, we wanted to use this quantum mirror to overcome that challenge, or to try and really witness this particle creation effect in a regime where the boundary condition changes non-perturbatively. Or you really split the cavity in two and unsplit the cavity in two, thereby changing the mode functions or changing the vacuum state of the electromagnetic field. So the way we wanted to propose to do this would be with, so this whole idea came about when our collaborator Rivka Beckenstein proposed this, came and presented at a seminar here, this quantum mirror made of a set of subwavelength atomic arrays. So using a Rydberg control atom, depending on the state of whether this control atom is in its ground or a Rydberg state, you can make this array either highly reflective or highly transparent to a narrow band frequency of light, resonant with the transition of the collective modes of these atoms. This corresponds to a superposition, so then you get literally a quantum mirror, or depending on the state of the quantum control, superpositions of transmissive reflective states of the array. So what we proposed to do then was take this quantum mirror and put it in the middle of a photonic cavity, and then get this state-dependent boundary condition structure for the electromagnetic field. So you either get these global cavity modes, or if you place the array at the right position, depending on the state of the quantum control, get these subcavities form on the left and right side of the array. And then you've got the Pauli Z matrix of the control atom. So now if you add the quantum controlled energy distribution to the Pauli Z matrix of the control atom, you see here that the distinct energy distributions across the two branches renormalize the energy levels of the control atom. So that means if I populate, as I switch in the reflective branch of the superposition, as I switch the array from transmissive to reflective, I pump that time-dependent boundary condition change, as in the dynamical Casimir effect I was explaining earlier, puts photons into the cavity. Those photons now get mapped onto a measurable frequency shift of the control atom. So you can read it out by now doing spectroscopy or interferometry of the control atom. So add a drive term and you get exactly that here. So this provides like a quantum advantage. So if you, the frequency shift or the particle content here gets boosted. So now that particle number operator is multiplying the frequency of the photonic modes, which for optical frequencies can be a factor of 10 to the 14. Compared to the line width, that would be, you can see here that this optical frequency factor now provide a quantum advantage, in that this really, if this particle content is really small due to a small boundary condition or a slow boundary condition change, this omega-1 factor, which can be as large as 10 to the 14 for optical frequencies, will really boost that signal above the line width by a factor of 10 to the 14 for optical frequencies. So that's really the crucial quantum advantage which makes this effect measurable. So if you do modeling of the response function, you get this atomic array. So what you get is that as you get this superposition of the control atom is in its ground state, and therefore the whole array is transmissive and just remain in the global cavity vacuum state. And then to lowest order the dynamics, you shift into this first to this reflective branch of the superposition, and entangled with the state of the quantum control, you get these subcavity modes in the ground state shifted out of the ground state by this factor gamma on omega here, which is the particle content produced due to the time-dependent boundary condition change. And now that particle content in that field state now gets mapped onto that frequency shift of the control atom. So I suppose one of the core points here is that this frequency shift of the control atom really gets this frequency shift of the control atom really becomes measurable in this regime due to this quantum, this boost by the factor ω1 relative to the line width here. And I suppose, as I was explaining before, it's part of the reason those previous experiments that came out from Chalmers in Nature that claimed to observe the dynamic Cook-Haslam effect were controversial is because, as I was saying, they can be interpreted as standard quantum optics experiments where you just do two-mode squeezing or parametric coupling of fixed cavity modes. Here we really split the cavity in two and unsplit the cavity in two, which is much closer to the original effect that was proposed by Moore. It also provides a way of really experimentally accessing quantum-controlled superpositions of Dirichlet boundary conditions. And then you get, by control-conditioned quantization or control-conditioned quantization of the field modes, you get this, so in one branch of the superposition you get a Dirichlet boundary condition at the array position. And this seems to be the first practical way to do a superposition of Dirichlet boundary conditions in a photonic cavity. So to summarize, much more I just explained the basics here for the purpose of a talk, but you can see much more details or microscopic modeling of exactly how you get this state-dependent Dirichlet boundary condition from the full microscopic interactions between the array atoms and the field modes. In the archive paper, and also my licentiate thesis, which is now online. And with that, thank you very much.
Thanks for the talk, Germain. Do we have any questions? Okay, in that case, we'll thank the speaker again.
Thank you. Are you presenting it at day one? You'll be presenting jointly. Mine and Jerzy. Good.
Exactly.
All right, next up we have Jerzy Paczos, who will be talking about gravitational wave imprints on spontaneous emission. Take it away.
Thank you, Acincia. Yes, so I will be talking about my most recent project with Navdeep, Sofia, Daniel and Magda on how gravitational waves affect spontaneous emission. Talking about gravitational waves and their interaction with matter, we typically consider a ring of classical test masses and a gravitational wave that travels in a transverse direction. Okay, the gravitational wave stretches and squeezes space alternately, which is reflected in the deformation of the ring. And this behavior of the classical test masses is behind most of the proposed and all of the existing detection schemes, including ground-based interferometers like LIGO and Virgo, pulsar timing arrays, or space-based interferometers like LISA. What we are interested in instead is how gravitational waves affect quantum systems, and in this project specifically, how they affect the quantum process of spontaneous emission. So let us first consider spontaneous emission in flat space-time. Imagine that we have a cloud of excited atoms. We know that because of the interaction between the atoms and the ever-present electromagnetic field, the atoms will not stay excited forever. Instead, they will de-excite and emit photons. And these photons will have frequencies from some typically narrow frequency range. And if the atoms were unpolarized, the emission will be isotropic. So it will be the same in all the directions. Now, what we have shown in our work is that the situation is a bit different in the presence of a gravitational wave. So the photons emitted can be from a different range than in flat space-time, and the frequency of the emitted photons will depend on the direction of emission. Okay, how did we show that? We took probably the simplest model of spontaneous emission. So we considered the atom to be a two-level system, which is point-like and follows a classical trajectory. And for the field, we took a massless real scalar field. Okay, and we, what's that? Okay, that's very bad. That's very bad, I'm sorry. But if there are no formulas, okay, now it works. Yes, and we consider the interaction between the atom in the field to be given by a monopole interaction Hamiltonian. So here epsilon is a small coupling constant, m is a so-called monopole operator of the atom, so it contains the hopping terms between the ground and the excited state. Here omega naught is the resonant frequency of the transition, and phi is just the scalar field operator expanded in terms of orthonormal solutions of the Klein-Gordon equation, UK star. Since we are interested in spontaneous emission, we assume that initially the atom is in the excited state and the field is in the vacuum state, and we write the state of the system at an arbitrary later time as a combination of atom staying in the excited state and field in the vacuum state with probability amplitude alpha, and atom de-exciting going to the ground state, emitting photon with wave vector k with probability amplitude beta k. And we can calculate these probability amplitudes alpha and beta using perturbative expansion of the evolution and express them in terms of these mode functions UK star. Here we will only be interested in amplitudes beta k corresponding to emission of a photon with wave vector k. And this expression is valid in any space-time in which we can formulate quantum field theory, and it's valid for any trajectory. Okay, so now how does the geometry enter the expression, the space-time geometry? It enters through these mode functions, which are solutions of the Klein-Gordon equation. If we recall how Klein-Gordon equation looks like in general curved space-time, we see that here is where the metric enters. Okay, and if we solve the Klein-Gordon equation in relevant cases, in flat space-time, we find that a convenient choice of the orthonormal modes are plane waves. So this is a plane wave corresponding to a photon with wave vector k and frequency modulus k. And if we solve the same equation on gravitational wave background, we find that the corresponding solutions are not very different. The only difference is this phase factor at the end. So this is a periodic modulation of the phase of our plane wave. So here we introduce this CK factor, which controls the magnitude of the modulation. Here curly A is the amplitude of the gravitational wave, omega is gravitational wave frequency, theta and phi are the angles of our mode, so our photon with respect to the propagation of the gravitational wave. Okay, so now we can use these modes to calculate the amplitude beta, and in flat space-time it's just a sinc function. So just to recall, sinc function is defined as sine x over x. We introduced here capital T as the duration of the evolution, and if we plot this function, it's just a single peak in the middle corresponding to photon frequency equal to the resonant frequency of the atom, and small oscillations on the sides. Okay, so we have a single peak in our spectrum, which is often very narrow. Now, if we solve the analogous equation in gravitational wave spacetime, the expression is slightly more complicated. So now it's no longer a single sinc function, it's a combination of different sinc functions with shifted arguments, okay? And the magnitudes of each term, they are controlled by Bessel functions. So what is really different on gravitational wave background? Well, in flat space-time, the emission was isotropic, so this coefficient, this amplitude beta, it was independent of the angle of emission. Now it's no longer true because this factor CK, it depends on the angles theta and phi. So now it will be different in different directions. So now there is some directionality of the emission. And the second thing is that since it is no longer a single sinc function, but a combination of sinc functions with shifted arguments, we will have, in the spectrum, we will have one peak in the middle corresponding to the carrier frequency, but we will also have sidebands. Okay, that's very nice. That's something we can look for in experiments, but it's of course natural to ask how big is this effect. We do not expect it to be very big because it comes from the gravitational wave, so we rather expect it to be tiny. But as I mentioned, the magnitude of the effect is controlled by this CK factor. And indeed, this factor is proportional to the gravitational wave amplitude, which is tiny. But there is also this other factor, modulus K over omega, so optical frequency over gravitational wave frequency. This can be huge, and typically it will be, it will always be huge because gravitational waves have frequencies up to kilohertz, those from the sources that we predict theoretically. So even if the overall effect is not large, it's much bigger than the bare gravitational wave amplitude. We have a big enhancement. So now we can ask, okay, if this is not so small, how many atoms would we need to potentially detect the gravitational wave? And to answer this question, we have to analyze Fisher information. I will not go into details here. You can find them in the paper, but we assume some idealized conditions. We assume that we can resolve ideally the frequencies and angles of the emitted photons, that we are only limited by shot noise. And we find that for low frequency gravitational waves, so for frequencies below or around 1 millihertz, we would need 10 to the 6, 10 to the 8 atoms to detect gravitational waves which are predicted to be there. Okay, so to summarize, we have shown that gravitational waves leave imprints on spontaneous emission, that they induce directionality and sidebands in the emission spectrum, and the effects are not that small. The requirements for detection are rather encouraging. And for the outlook, now with collaborators, we analyze stimulated emission, so what happens if we have non-vacuum states of the field. We look at collective effects. This is the direction that is mainly developed by Navdeep and Magda. And also with Patryk, we look at simulating the effect of a gravitational wave in cavity QED systems. You will hear more about that in Patryk's talk. That's it. Thank you very much. And if you are interested, I encourage you to read the paper.
Thank you. Do we have any questions for Jerzy?
So you said 10 to the 6 or 10 to the 8 atoms, more or less. And do you need to arrange them in a specific way? Do you just...
No.
Is it okay to have a guess? Like,
Yes.
what's the... Really?
Yes. A cold
Wow.
atomic cloud, independent atoms. We do not include the technical noise, which probably will be critical. Probably, I'm guessing now. But if you are able to suppress the technical noise, 10 to the 6, 10 to the 8 atoms.
Impressive.
All right, let's thank the speaker.
Yes.
All right, so for the last talk of today, we have Patryk Michalski, who will be talking about simulating gravitational wave effects in strongly coupled atom cavity systems.
Thank you very much. So the starting point of our work when I came to Stockholm in January for a month-long visit was exactly the paper that has just been discussed by Jerzy, which suggests that it is, at least in principle, possible to detect the effect of gravitational waves using point-like two-level atoms by looking at their spontaneous emission spectra. Now, the question we aim to answer in our work is whether it is possible to simulate this gravitational wave effect if we, instead of considering modulation of the electromagnetic field induced by the changing metric, put the atom inside the cavity and move one of the mirrors, effectively modulating the boundary conditions. So let me briefly introduce the model we employed in our work. We start with a two-level atom with ground state, the excited state, and the transition frequency omega A. We put it inside the cavity, which has a resonant frequency omega naught, and we assume the atom to be located exactly at the antinode of the resonant cavity mode. And we assume the frequency of the mode to be slightly detuned from the atomic transition frequency by delta naught. Now the atom interacts with the electromagnetic field inside the cavity at a rate which is determined by the coupling constant G0. And for simplicity, let's assume that we prepare our system in a state in which the atom is in the excited state and there are no photons inside the cavity. Now, it turns out that when the coupling constant G0 is large enough compared to the dissipation rates, which we for now neglect completely, the probability of finding the atom in the ground state after some time t exhibits an oscillatory behavior which is known as Rabi oscillations, which is given by the following formula with the characteristic frequency also called Rabi frequency, and whose amplitude is determined by the ratio between the detuning and the Rabi frequency. So now let's see what happens when we start to move one of the mirrors in the cavity. And to be specific, we assume this one mirror to move harmonically with frequency omega and an initial phase phi. And we also assume the relative amplitude of this oscillatory motion to be very small, so that we can treat this parameter as a perturbative parameter. And as a consequence of the changes in the length of the cavity, the resonant frequency of the cavity also changes to first order in A. It is given by the following formula. And assuming that this modulation is adiabatic, meaning it is slow compared to the time it takes the photon to travel from one end of the cavity to the other, we can take the field mode, resonant field mode, to follow the resonant cavity frequency, so that also the detuning is time dependent. And this to first order in the parameter A parallels the effect of gravitational wave on the frequency of the electromagnetic field for the specific mode. Now let's see what happens to the probability of finding the atom in the ground state after time t. In the perturbative expansion, this probability naturally splits into the equilibrium contribution, which corresponds to the Rabi oscillations, and the correction, which is proportional to this small parameter, but also to the ratio of the resonant cavity frequency omega naught and the modulation frequency omega, and this ratio can be large, as in the case of gravitational wave-induced modulation. And this function f, plotted here on the right, is resonantly enhanced for the Rabi frequency capital omega naught equal to the modulation frequency, which recovers the first sideband in the spontaneous emission in the gravitational wave case. So now let's compare our result with the gravitational wave imprints on spontaneous emission. So on the right-hand side, you can see the average number of photons emitted into a fixed mode of the field, which up to first order in A also decomposes into the equilibrium contribution and correction. Now the resonant mode, cavity mode frequency in our case corresponds to the frequency of the modes in which the photons are emitted in the spontaneous emission process. The mirror modulation frequency corresponds to the frequency of the plane gravitational wave. And finally, our Rabi frequency corresponds to the detuning between the atomic transition frequency and the frequency of the mode to which the atom emits. So it seems that, at least in principle, our setup is able to recover the first sidebands in the spontaneous emission in the gravitational wave case. However, there is still one issue to be addressed. Namely, I recall that the correction is resonantly enhanced, and it corresponds to the appearance of terms linear in time in the expression for the function f. And this is problematic since it implies that our perturbative solution works only for times that are smaller than the characteristic long time scale given by the inverse of a times omega naught. So we solved the evolution once more, this time using the multiple scales analysis, which allows to get rid of those problematic linear terms. And here you can see the lower and upper bounds on the probability correction for a specific choice of the initial phase and the ratio r, plotted in the long time scale. In gray, you can see the bounds on the perturbative correction, and in red, you can see the bounds for the multiple scales solution. So, as confirmed by numerical simulations, this multiple scales solution gives a very good approximation of the system's evolution at later times, and it also shows that it is sensible to look for these longer times of interaction between the atom and the field, since the correction anyway accumulates up to some point. Okay. Now I recall that we neglected all the dissipative rates in our model, and to evaluate whether this model can be used to observe our effect experimentally, we have to take those possible loss channels into account. And the first one is that the atom can decay by emitting a photon that is not coupled to the cavity mode at a rate gamma. And some photons may also leak out of the cavity at rate kappa. So the full set of requirements for any feasible platforms to detect the effect are first the adiabatic condition that I discussed a moment ago, the perturbative condition, and we also want to have a coherent interaction over many modulation cycles, so the modulation frequency has to be way larger than the dissipative rates. Now we looked at three platforms that seem natural to implement this setup, first of which is optical cavity QED, which seems to be the most literal. However, it turns out that to satisfy the perturbative condition, the amplitude of the length modulation is so small that to describe the system completely, one would have to consider also quantum effects in the mirror's motion. Additionally, since the decay rates of optical cavities are not necessarily small compared to available modulation frequencies, it is also not possible to get coherent interaction over many modulation cycles. The second platform is microwave cavity QED, in which the cavities are a bit larger, not in the micrometer but centimeter scale. So here the perturbative condition can be satisfied. And the question whether coherent interaction over many modulation cycles is possible we are still looking into that now. And finally, the most feasible platform we are able to find is Circuit QED, which is an analog platform in which instead of a literal cavity, you have a one-dimensional resonator. There, both the adiabatic and the perturbative conditions can be easily satisfied, and these setups have also been used to demonstrate, for instance, the dynamical Casimir effect that Germain mentioned. So modulating the cavity length is also fairly easy, and one can achieve much larger modulation frequencies than in mechanical modulation. And thanks to lower decay rates, it is also possible to achieve coherent interaction over many modulation cycles in this platform. So to sum up, we have shown that gravitational wave effects can be simulated in these strongly coupled atom cavity systems. And it seems that the requirements of the setup, especially in the circuit QED case, are such that this experiment may be within reach of current technology. And this would enable to study the simulated effects, gravitational wave-like effects, and to identify any challenges before moving on to designing quantum sensors for actual gravitational waves. Thank you.
All right, thank you for the talk. Do we have any questions for Patryk?
Have you been in touch with any experimentalists to actually implement these in practice? Or are these, at this stage, just theoretical works that use experimental
At
values?
this stage, we haven't consulted any experimental group, as far as I know.
Okay, let us know when you do. It seems very interesting. Thank you.
All right, let's thank the speaker again.
So just closing remarks. Okay, well, thanks everyone for being here in this first edition of the RQI Circuit. So next week we'll be in Vienna. I mean, I'll be in Vienna, and at least 2 more people that attended today will be there too. But well, if you're around, feel free to join. If you're not, basically, we're going to have the broadcast. We'll hear a lot about quantum reference frames and things like this. So hopefully you'll be able to watch online. Any other announcements? Yeah, so there was no audio in the beginning of the broadcast, so every single information that I gave to you guys was just for you guys. And important, we have this scientific art. So Scientifica is this initiative that started here in Nordita, which is basically science outreach talks with fika, and fika is basically the notion of having coffee with sweet baked goods in Sweden, or coffee breaks, if you will. So basically, Scientifica is an initiative that usually Nordita hosts here on Friday evenings. But especially today, we have the Scientific Art, which is this initiative in which they mixed art with science. And this is being hosted at Provia, which is the restaurant that is literally across the street here. So everyone here is welcome to join, and we can just go, and apparently there's a reception. And we've been formally invited, so we're not going to be breaking any rules by doing this. Just before we go, I'd like us to please thank the 2 local organizers, Jerzy and Germain, for putting this together.
And thanks to Rick for the initiative again. Thanks to all the speakers for the great talks and for all of you to come here and follow.
All right, thank you.
And if you are not joining Scientific Art, I think there is still a lot of fika after the coffee break. So.
And also I'd like to have the sandwiches as well.
Yes.
Okay.
Yes.
Perfect. Thank you.
Thank you.